which we will have to transfer the technologies, right? And this will lead to large volume. So we don't plan large volume inside the pilot line, but we will show the scalability of the technology. So next one. So the origin of the pilot line, we come from somewhere. So we come from different pilot lines existing or which have ended in Europe, right? And you have all of them here, and I guess you know them. And the idea is to unify the ecosystem, right? Unifies and standardize these photonic integrated technologies, and from chip design to fabrication through packaging and testing. And especially the second, let's say, bold objective, grand challenge, is to increase innovation capacity and lower the production barriers for the European industry. As I said, the pilot line is quite broad in terms of material systems and technologies. And in fact, we cover what we believe to be, the full wavelength spectrum. And we plan to offer monolithic platforms and hybrid platforms, right? And I guess you see here most of them. There will be some more. And eventually, so we should try to unify everything and offer PDKs, ADKs, and TDKs on all those technology for all the wavelength range and applications that are foreseen today and in the future. We are a distributed pilot line, so we are essentially made up of nodes. Each node actually that you see here is led by one specific entity. For example, design and testing reliability by TOE, packaging by Tyndall, the EIC integration by MEC, the hybrid integration by UPV, the prototyping and demonstrator by ICFO, and then also ICFO is responsible for the overall coordination together with other partners of the pilot line. We have essentially 5 monolithic PIC platforms: silicon carbide, and this is FPK with poly-D, silicon VTT, silicon nitride and aluminum oxide, and this is mainly SESIC, indium phosphide TNO, and germanium on silicon is the Polish group VUT in Warsaw. The operations are let's say, quite standard, but they are centralized, right? So we will have a gateway, and the gateway is a little bit the center of the operations. And essentially, we have all those activities on the left that I mentioned before. We will develop within the pilot line PDKs, ADKs, and TDKs that we will assess, we will benchmark through the demonstrator, and the end user, right? All these small companies that cannot invest in such a large amount of capex, and they really want a fast, track to prove their technology, will go to the gateway, and the gateway will distribute the work. And the final result is that the processes developed should be transferred to industries, to manufacturers, which are able to scale the production for the end user. We have different phases. So essentially the pilot line, if a negotiation goes well, we are still negotiating it, and it is a quite actually cumbersome and articulated process, but we believe that we are close to the end. And if everything goes well, we should start in May or June 2025. The grant period, so the funding for both building the pilot line, the CapEx, and also for setting up the operations and operate it, will last 5 years. So the initial grant period by the CHIPS JU is 5 years, full cost. And then we are supposed to become sustainable in the following years. And this is possible, especially because we plan to engage very soon with industries, right? So for us, our main customer, I said before, are the end users, are the companies that need technologies and platforms. And in the long term, we will need to raise CapEx for the pilot line operation phase. And we already have a quite large amount of end user actually in the pilot line. To simplify what we decided, we made this initial distinction: designers, manufacturers, suppliers, and vertical integrators. For us, those are all end users. A typical example is a supplier, for example, of equipment that works with the pilot line to develop their equipment. A designer is essentially an end user that works with the pilot line to assess their design. The manufacturers that work with the pilot line to take on the scalable processes, and the vertical integrators, we expect to have many of them in all the different applications. We have already received a significant support in terms of letters, and we have started to talking to the end users, and we will soon also tell openly what our plans are for the open access, even though the open access needs to be built also during the pilot line. But we will try to open the access as soon as possible with the existing essentially equipment. So here are the work packages. As any project, we have work packages. I don't go through all of them, but we have technical work packages, which are quite standard, let's say. And then we also have dissemination, exploitation, and collaboration work packages, and especially those contains training. And we position ourselves with respect to the other pilot lines. I already mentioned the existing ones, and then there are 4 more within the chips JUs. Nano IC, that is about 2 nanometer node, FAME 7 nanometer, WPG is wide bandgap semiconductor, essentially is power electronics, and Apex is heterogeneous integration, mainly electronics. So there is a clear relation in terms of use of the technology and also complementarity with the other pilot lines. And also we are instrumental to build in the future the photonics for quantum pilot line. I'm sure you're aware there was a call that closed, I think, in January, and the selection of the framework partnership agreements is ongoing. So essentially, with this slide, I'm done.
Okay, Valerio?
Yes, I can hear you.
Okay,
yes,
okay. Okay, so you are done. Okay, it was faster than I had thought. Okay, thank you very much, Valerio. We can thank you, Valerio. I hope you can hear the applause.
Okay, good, thank you.
Okay, so now it's time for questions, if you have any. Be aware that it's your only opportunity to talk to Valerio since he couldn't make it to come.
Hi there, Victor Sergio from New Quantum in the UK. I'm interested in how and who will be aggregating all the PDKs and ADKs that will be generated throughout all these 5 and 10 years, because, well, I feel there's going to be a lot of benefit on that particular group or person.
So the beneficiary should be the end users, right? So those are processes and that are developed within the pilot line, but then they will be made available to the end users. So, and this is regardless, you know, this is in Europe preferentially, right? But the CHIPS EU is also establishing guidelines to collaborate with industries that are not European, but are essentially operating in Europe to some extent, right? So there will be different types of end users, let's say.
Sorry.
So if I'm an end user in the industry of Europe, I will have full and free access to all the PDKs and ADKs.
So you will have preferential access at a discounted rate, correct? So, and then we also expect parallel calls, right, for the end user to work with the pilot lines. Yeah, so that means, you know, also public support to foster the interaction, especially in the initial phases of this endeavor, possibly during the first 5 years, right, until all the PDKs are established. And actually the PDKs in principle should go to the design platform. Okay, so from all the pilot lines, right, should end up in the design platform. That is another project of the CHIPS EU once consolidated.
Thank you.
Thank you very much. Any other questions?
Hello. Hi, Valerio. This is Christopher Dirdal from Sintef in Norway. And I'm here today representing Norway's CHIPS Competence Center. This is super interesting, and I'm just wondering, how does PIX Europe foresee collaboration with the CHIPS Competence Centers? Have you thought anything about this?
Yes, of course, we are thinking, right? So the requests from end users, right? We expect many requests to go through the competence centers, especially the first contacts, no, until the end user is in contact with the pilot line, right? And this the competence center should foster this, right? And also we expect that the competence center will also enhance the actual training on the machines within the pilot line. So imagine the typical situation is the competence center, you know, gives, let's say, more theoretical training to some extent, right? And then the pilot line should complement with hands-on training for end users. So I guess that the role there of the competence center is really to enhance the interaction with any type of end users and the ecosystem, right? So in that respect, it's true we don't have Norway for the time being in the pilot line, right? But through the competence center and also the connection to the companies like you, I think you know, we will make sure that the pilot line goes beyond essentially the countries that are actually participating.
Very good, thank you.
Okay, thank you. This is the last question.
Thanks, Valerio. This is Mariam from Ligentech. I would like to ask you if you see that there is enough business market behind all the offered technologies that you are aiming to develop within the pilot line.
Actually, this is a very good question. The pilot line, Maria, was born to establish, you know, a unified technology platforms in Europe, right? So, and the reason for that is the need that many startups, spin-offs, and small medium enterprise, you know, have to essentially accelerate their product development. Okay, so this is, your question is a bit the chicken and egg question, right? So, you know, I guess that the photonic integration, right, to be pervasive, on the one hand, needs the market pull, right, but also the technology push is important. So everything at the end should come together, and essentially there should be, of course, a market out there that is addressed by all the small, medium enterprises, right, and eventually supported by large manufacturing. And you can be also one of them, sustained by continuous development of PDKs and ADKs and TDKs by the pilot line. The pilot line does not pretend to do, mass volume. Manufacturing pretends to prove the scalability. So in that respect, we don't feel we are in competition with companies that actually are manufacturing. We are actually helping them eventually to essentially consolidate the processes. Of course, within a European context, so the sovereignty is a very important aspect that goes with it, and is not only about market.
Thank you very much, Valerio. Thank you. I think Maria was okay with the answer. Yes. Okay. Thank you very much. So we can.
You're welcome.
Thank you very much for for your participation, even though it's online. So we can thanks Valeria once again.
Very good. Thank you. Thank you. Bye.
Bye, Valeria. And then we can move to the next speaker. We have make a little change in the program. So the next speaker will be Joaquin Faneca from CNM, and Pascual will move to the last part of the session, okay? So. Joaquin?
So good morning to everyone. First of all, I would like to thank the Photonic Integration Week organizers for inviting us to give this talk, and also to push the ecosystem in Spain and also in Europe about photonic integrated circuits. My name is Joaquin Faneca, and today I'm going to talk about the silicon nitride monolithic integration in PIX Europe. So first of all, I will put you in context in where are we inside of an institution. It's called the Spanish National Research Council, the CSIC. Then I will describe the center, the CMOS compatible facility that we have, then the silicon nitride technology that we offer, and also we will talk about the PIX Europe silicon nitride. And finally, we will just give an overview of how are we involved in the CHIPS Act and the CHIPS WHO as an institute. So we are part of the Spanish National Research Council. We have more than 100 institutes around Spain. We are in Barcelona, but the good thing here is we are a research center that we operate with budgets around 1,000 million euros in total, with some incomes that comes from the government and some outcomes, of course, that comes from personnel and buying equipment or infrastructure. These are the report of 2023, and which is just the papers that have been published, but for us it's just interesting the ones that are from engineering and technology, which is around 30% of the publications. This is our equality plan, quality gender plan that we have for the CSIC. So we are trying always to keep almost a balanced ratio between men and women. And as a National Center of Microelectronics, that we are part of this national institution, we were created in 1985. And as a National Center of Microelectronics, then it was created 3 different centers, one in Seville, one in Madrid, and one in Barcelona. So the Seville one is just orientated to the analog mixed IC design. Then the Madrid one is orientated to compound semiconductors for nanoscience technology. And ourselves in Barcelona, we have a clean room in which we are based on silicon, micro, and nanosystems. So we are based in the autonomous campus of Barcelona, in the middle of a small forest there. And we have like a scalable and nano microfabrication technology. So we are orientated to electronics, but also to photonics, so we can process both. And then in the microfabrication facility, we can like do R&D or do small series production. In our institute, the Institute of Microelectronics in Barcelona, we have around 237 people working there. We operate with around 13 million euros, and we have 8 research groups in the institution. We normally apply for 8 patents per year, and we have like created 14 spin-offs, but 9 of them are still active. 5 of them are not going yet. In the cleanroom facility, so we are since 1996 the research largest cleanroom in Spain, and we are part of a distributed ICTS, which is an infrastructure, like a single infrastructure, and we are part of a network. It's called the Micro Fabs, that is together with the NTC in Valencia and the ISOM in Madrid. We are having also the certificate for ISO 9001. And this is the facilities, clean rooms that we are having in the center. So we have 1,500 meters square clean room. We have like around 6,000 meters square of facilities and services apart from the clean room itself. We have running inside there more than 190 process equipments. We have just technicians and engineers that work only inside the clean room. We process around 2,000 wafers per year, and we normally go from concept to market in some cases. And this clean room was like inside, we were developing like silicon nitride technology for photonic integrated circuits. That's the one we offer. We were going from the visible to the mid-infrared. We were collaborating with VLC and also UPV since quite a while. And we cover different ranges of the spectrum, different cross sections in the near-infrared. We do also thermo-optic tuners to do passive dynamic photonic integrated circuits. We can also see here that we can always do the trenching in order to get to the top of the waveguide as well. And we can put like there the thermal heaters. We have also spot size converters to have like low loss chip coupling between the different areas of the chip. As a platform, we have like 2 different approaches. We have like the multi-project wafer approach, in which has its advantages and disadvantages, also the dedicated or custom process approach. In the multi-project approach, what we have are the advantages that you are eliminating the need of having your own fab, of course. I mean, you can be a fabless company and you can produce your picks with our institution. If you participate in the multi-project wafer, you will probably reduce significantly the cost per cycle. And if you work with design houses for multi-project wafers, they have already developed the PDK, so they have their own libraries, so you will reduce the number of design cycles, and you will avoid the cost of having people that needs to have expertise in the topic or to have licensing costs. Instead, if you have like a dedicated or custom approach, you have like to have long cycles, because you need to develop every building block, you need to test it, you need to refine it. That will need also licenses to have multiple design software packages. That will require expertise from people to do all these designs. So at the end of the day, what you have is a larger investment, but you win in other aspects. So basically, you can customize your process of fabrication, you have more flexibility, and this is something we operate as well, and we normally do around 3 wafers per year that are customized. So this one here for the multi-project wafer, we have developed this together with VLC Photonics, the Hitachi Group company. That is our design multi-project wafer broker. So this is the fabless user, so they contact them, they do like all the tape out, and then we do like the fabrication. All these like end up in being mentioned by Photon Delta recent study of 2024, in which they were talking about the global silicon nitride map, in which we were as an institution situated in the manufacturing technology and also in the foundries. But apart from us in these 2 places, we have different people like VLC Photonics here and all different partners in Europe that merge the ecosystem. This is important because all these research institutions, like together, we were pushing to give birth to this pilot line, or what it's called the project, the PIX Europe. So it's distributed, as Valerio was explaining to you, like different monolithic technologies, hybrid platforms, packaging, testing, etc. So in here, what we are focused on is basically in the monolithic peak platforms, and we are even more focused in the silicon nitride, even though we are also like coordinating the aluminum oxide that is doing by the University of Twente. We are doing all this together with Twente and Cealetti, and these are presenting like some challenges, the silicon nitride right now. So basically what we have is like the current state of silicon nitride, we have poor light generation, so silicon nitride monolithic platform itself is not possible to generate light at the moment, and we are tackling this challenge with hybrid integration, but not with monolithic, so that's what we will say here that it will be still poor in PIX Europe, but with hybrid integration that Pascual will explain you later, it will be tackled. Then we will try to improve like some of the characteristics of modulation, detection, low loss passive. So these are some of the characteristics that PIX Europe will try and will improve during the 5 years. And another aspect that we need to improve as well is the scaling and manufacturability. So we will improve the integration density. Also, we, as Valerio was mentioning before about the scaling, we will go from 150 millimeters wafers up to 300 millimeters wafer. We will improve the capacity foundry in terms of like different processes, different wafer sizes, and then also we will try to improve the technology and commercial manufacturability. So there is two aspects here in silicon nitride. We will talk about the silicon nitride near infrared, and in the near infrared we want to improve the functionality and the integration of the peaks, and here we focus in 3 different aspects. So we talk about material, components, and the technology itself. So when we talk about material, we will play with the stoichiometry of the silicon nitride, so we can tune the refractive index properties. And apart from that, we will tackle thick, thin, and ultra-thin silicon nitride peaks. In other way as well, we will develop components with edge couplers, modulators, frequency comm, and multi-level components between silicon and silicon nitride. And then in technology, we are targeting to reduce losses, to improve confinement, to improve the integration density and the scalability as well. So this is an example of functionality that we will be developed in PIX Europe, in which we have like modulators. They are different ones and different characteristics. So we have like thermal tuners, which are the most used right now for the compatibility. But there is different characteristics: CMOS, power consumption, footprint, speed, the yield, and all of them has different characteristics. And these ones are some of them that will be developed in the PIX Europe. Some of them will be monolithic integrated. Some of them will be back-end of the line processes, and some of them will be hybrid. But these are some of the examples that they will be targeting in the PIX Europe. Apart from the near infrared, another objective of this pilot line is to also expand the wavelengths of the platform. So not only stay in the near infrared, so also go to visible and the near infrared. And here we have like in the visible, basically we would like to have like universal waveguides, single mode waveguides that can support like all the wavelengths in this range, that they will have high confinement factors, building blocks, create the components library, define the PDK, and when we have the passives done with the silicon nitride, we will try to integrate hybrid building blocks to have like actives as well. Apart from the nitride, in this wavelength range, we will also work in aluminum oxide and silicon carbide. Silicon carbide operates from 600 nanometers upwards, so only in the red part of the visible, but it will still be operative in these wavelengths. And in the near infrared, we will target to integrate the 2D materials with the silicon nitride. We will do thick and thin silicon nitride in this area, and the same, we will create the components library, the PDK definition, and also it will be studied the aluminum oxide and the silicon carbide in these wavelengths. So as also Valerio was showing to you before, we are not only talking about silicon nitride in PIX Europe, we have different technologies. The goal is to cover all the spectrum, to cover also different applications and demonstrators. And apart from silicon nitride, we have silicon carbide, indium phosphide, aluminum oxide, silicon germanium, and SOI. So an important part is also to scale the wafer size and going from TRL, as Barry was saying, from 4 to 6, and then the companies probably will do the volume manufacturing. So here we have we will be working 550 millimeters, but then University of Twente and Thealeti will scale these technologies up. And this will be done also not for silicon nitride, but it will be done for every other single monolithic platform that I have shown before. Here is the methodology that probably will follow, and this is the monolithic integration materials we have been talking about, like the silicon nitride, carbide, silicon germanium, indium phosphide, alumina, lithium carbide. So first of all, you need to do the designs and simulations to determine in which wavelength you want to work, visible, near infrared, or near infrared. Once you have defined this, you do the process development. So you do also the parametrics test in the fabrication. So you need to validate your technology, you need to validate the fabrication processes. Once that is done, the passive devices with the monolithic, you can go to hybrid integration. So you can do a PIC plus PIC or PIC plus electro-optic modulators. So you have your hybrid technology. And all this will come out with a PDK, the process design kits that will come back to the design. After the hybrid, you can do like the dicing and functional testing. So you will test the devices and you create the TDK, the test design kit, that also fits the design and simulation. Once all this is done, we also have the assembling or the packaging with the interposer and the chiplet, which gives you the ADK, the assembling design kit. So always we talk about process design kit, test design kit, and assembling design kit. All this needs to fit the first design and simulation to have like a circle. When all this is done, you can do your PIC system, which you need to have like reliability testing. And it will come out with a demonstrator to prove the compatibility between the technologies. And this is also like one of the questions that was asked before about the PDKs. So basically, this is an example. So you have different PDKs, so they need to be compatible. That was something that it was asked before. And imagine you have like a visible PIC. You know, you do your design and simulation with the visible components. So you have your building blocks technology. What you do after that is you do your PIC fabrication with different building blocks integrated to create the system. And if you want to have an hybrid integration after that, what you need is to come to the hybrid PIC. So probably you have here another PDK. So these two PDKs must be compatible if you want to have both technologies. That's the key point that it was asked before, and this is important. But all this should be like available in, as Valerio also mentioned, in the Chips Who Design Platform Hub, which is a project created for the designs. We have demonstrators, more than 4, but I just put you some of them and only the ones that the silicon nitride is involved. So basically here we cover different wavelength ranges, so visible, near infrared, and mid infrared, and we also want to demonstrate the compatibility between the technologies. So we have like an optical space switch in which we will do like silicon nitride and thin film lithium carbide, visible light engines to prove the peaks silicon nitride in the visible range, the mid infrared in which we will do also to integrate 2D materials with the nitride, and then the programmable photonic processor that will be in the near infrared. This is important because these demonstrators need to prove the interoperability between the different research centers and the different technologies. So that's why the demonstrator is the first proof that all the technologies are available and compatible between the different research centers. And just to finish, from the point of view of our institution and the involvement that we are having with the European Chip Guide and the Chips Who, as we have here, we have like the design platform in which we are involved. Then it has been created by the Chips Who also the competence centers in which we are part of the Micro Nano Spain and the PIX Spain Competence Center. And between the 5 pilot lines that also Valerio mentioned before, we are participating in the Apex one, which is the heterogeneous integration, mainly electronics, and also the PIX Europe, that is the one that I have explained right now. Let's see like if we are involved or not in the quantum. And that's all. Thank you for your attention, and if you have any questions, I'm more than happy. Thanks.
Thank you very much, Joaquin. Any question from the audience?
Thanks for the presentation. My name is Mohammed Bila from Wenger Automation, Germany. When you mentioned about the hybrid integration, which technique do you use basically to integrate the 3.5 light sources? Because you mentioned this remains as a challenge for both platforms.
Yeah, I think, I mean, I can answer, but I think probably Pascual will give you the talk like later about all the hybrid integration, so I don't want to make like, but we have different techniques, you will see, like 3 different ones, and he will explain you all of them specifically probably in the hybrid integration part of the PICS Europe.
Thanks.
Thanks.
Hi, Joaquin. This is Mariam again from Ligentech. If you can go to slide 11, because I'm a bit curious on, you showed the current state and the outcome from the PICS Europe. I don't know if you could provide some numbers on your KPIs for each of like the low losses passives, or even, I mean, you showed on a different slide, yeah, for the demonstrator on slide 20, if you have something in mind that you could share with us.
In terms of like losses, in terms of integration, in terms of like, we're talking about confinement factor of more than 90%, losses smaller than 0.1 dB per meter in thin silicon nitrides, and speeds about gigahertz. So that's some of the data with the silicon modulator, silicon nitride platforms that they are developing also in Theality. So I don't know if this answers some of your questions, but if you want to have more specific information, we can have a chat about the characteristics.
Thank you.
Thank you.
It's also important to point out that this pilot line is not only for having the most quick modulator or the lowest loss, is to have to provide Europe like a technology that is robust, that is repeatable, and is able to feed the prototypes of the industry with a TRL6. So this is also, Valerio mentioned that, but I think it's also important to point this out.
If there are no more questions from the audience, okay, thank you very much, Joaquin, for your comments and your speech. I will say something that I forgot to mention, that I never say thank you to our sponsors, who are VLC Photonics, Nanoscribe, and Bullnet Capital. Thank you very much for the sponsorship, for sponsoring this event. Thank you for all of them. And now our next speaker is Guillermo Carpintero, and he will give. Thank you, Guillermo.
Okay, thank you very much for inviting me to have an excuse to come to Valencia and to meet all of you. It's always a pleasure to meet the photonic ecosystem. And I'm also part of the PICS Europe pilot line. And we are at the UC3M, we are responsible for providing the high-frequency interfaces that we want to provide as a node in this pilot line. And basically, this is because the high frequencies have had a very useful tool with photonics. Basically, because usually the high frequency is connected through coaxial cables, and actually the optical fiber is a much lower loss media to send the signals. And actually this is was early, this is a publication in '87, comparing the losses of coaxial cables, rectangular waveguides, which are the interfaces commonly used in the RF industry, compared to fiber. And actually people immediately saw that, why I'm going to use coaxial cables if I have actually 2 orders of magnitude lower loss if I use fiber. So this has actually comparing the two media, what you come up with is that use not only the losses that are better, but also an important part is the bandwidth. And that's what is actually driving the internet today, because you actually have very high speed highways on optical fiber. And from this, basically, optical components have been evolving. And now, actually, the photonics is on this end of the spectrum, and the electronic has been moving in the lower end of the spectrum. But of course, needing higher frequencies has pushed the signals that electronic is handling higher up. Actually, now what we call closing the gap, because the signals that can be handled in electronics are moving up into the terahertz region. That is in basically 10 to the 12 gigahertz, which is beyond the gigahertz. And when you talk to people in electronics and you tell them terahertz, basically it's a frontier they never thought they would be getting at. And of course, they are scared of the losses. And that's when usually photonics, you can always say, okay, no, but we have photonics to deal with these signals. For that, you need to take these high frequency signals of the electrical domain into the optical domain, and that can be done because actually the components that I showed you that we need before, the components that interface with the electrical signals have been increasing their bandwidth. They are able to handle higher and higher frequencies, optical modulators up to 500 gigahertz. That's already in the terahertz range. And the photodiodes have been a way to generate high frequencies for a long time. And when you shine them with the appropriate optical signals, you can actually generate up to terahertz frequencies because their bandwidth is really unmatched by any other component. The problem is that, okay, now I have photonic components that have interfaces, electrical interfaces that are reaching within the hundreds of gigahertz. And that's really a challenge. That is putting a lot of pressure on the interfaces because yes, I can transmit signals without loss, but how do I get it into this component? This component has this bandwidth, how do I get the signal into that component? And the thing is that it's needed because higher frequencies are not just needed by internet, now they are needed in computing. Artificial intelligence, this is a recent graph of what are the requirements that are needed in terms of bandwidth in memory to be able to do artificial intelligence computation. You actually need to train models, you need to feed a lot of data, usually images, and you need to process this. And actually, if we go to this graph, what you actually can see is the computational cost of training is increasing enormously. This is the main bottleneck for the artificial intelligence. And actually, the problem that this is not related to the interconnect is the problems of the computational cost. And this is moving data from CPUs to GPUs. Actually, this is moving the data from chips to chips. And this is where the problem is actually reaching because the computational speed is increasing, but how we can move the data between the chips is stuck. And this is because the interfaces have not evolved. We are using the same interfaces that we've been used for ages. And some years ago, because actually this is from 2019, but you will start seeing this graph if not, if you haven't seen it any before. Because actually this is the DARPA figure of merit. Actually, they are not, they have overcome the bandwidth. They are talking about the bandwidth density. Is how close can I put interfaces that can allow me to transfer data, and what is the energy that I need to drive those interfaces. And in terms of the distance, what you actually can say is that, yes, optical media has been a solution to transfer high-frequency signals, but only if the distance was long enough. For shorter distance, because, well, shorter distance means that your interfaces, if you have very high loss, The distance is very short, so the total loss I'm going to have is not going to be very big. So actually, this is comparing with this figure of merit, the different technologies. Standard electrical RF interfaces are able to reach down to 1 meter. From 1 meter is optical, and that's why within chips, basically the technology that has been used is electrical, is copper, and beyond 1 meter, then we move into optical. The interfaces that have been used to connect these chips basically is microstrip lines, some electrical transmission lines. You have interfaces at the chips. Problem with these microstrip lines is high losses and low power. And these high losses means that, okay, if the distance is short, I can deal with it. The problem is if we keep increasing the frequency. That losses cannot be ignored anymore, and it's starting to be a problem to connect two chips with electrical interfaces if you actually want to go beyond 100 gigahertz. And well, there are other interfaces that connect out of the chip, and these are even worse because coaxial lines, actually the losses are increasing, but you cannot integrate this. And actually the bandwidth is actually limited below 100 gigahertz. And if we move to waveguides, that's even worse because this is basically banded. So what we find is there are actually no real alternatives to microstrip lines. If we want to connect chip to chips, we have to work with this in copper. But as we go higher in frequency, this is a barrier. And this is a barrier that we have to overcome. And of course, people have been thinking, can I move optics downwards? And that means, can I integrate photonics interfaces so I can connect, make it cost efficient to interconnect devices with optics? That is being considered. Silicon photonics, thin film lithium niobate are actually providing engines that you can integrate these interfaces and connect them with actually fibers or bad coupling the devices. Actually, what you can see here is the lasers with the modulators in silicon photonics to make, this comes from Intel, an optical engine for AI computing. Actually, NVIDIA is the company that is providing the most advanced engines. They are connecting GPUs, CPUs with copper. They see very difficult, they want to stick to copper. They don't see a reason to move to optical. So right now, this is the battle where we are. It's how we integrate high frequency with high frequency electronics with photonics. Current devices is the small form pluggables. The small form pluggables is actually now the most compact electrical photonic device, in which you basically, it's what you have in the data centers, and you connect this at the terminals to connect the racks. And what you have is the electronic devices on PCBs, and that's where you mount the optics. And from there, you have your optical device. But still, you need an electrical interface that connects these two elements together. And to the technology that is supposed to be the solution, which is co-packaged optics, where actually electronics and photonics will stand on the same motherboard. Actually, there is still a way to do this because this must be economically viable. And now we are not talking about heterogeneous integration of optical devices, it's opticals and electronics. And usually the electronic devices have characteristics that photonics don't like the power consumption and the temperature increase. That if you put an electronic CPU or a serial SERDES, a serializer, the serializer, next to a photonic device, the heat that this will dissipate probably will affect the photonic component. So this is an issue, and not just in the RF losses, it's also a thermal issue, and the finding out what is the right substrate in which you can mount these devices all together. And these are the challenges that we are actually addressing. One of the demonstrators is actually this short, small form pluggables, and we are looking at the substrates on glass where we can mount the devices. And the problem is the interfaces. And these interfaces means that, okay, I'm going to have an RF interface in the electrical, in the optical. I'm going to put them close together, but I still need to connect them. And to interconnect them, basically, you will have your chips on a substrate where you will have a transmission line, probably, that you have to connect. This is the problem. This length is a problem. This interface that you actually have to make electrical connection between chips, it's a problem. And the substrate that you have here, it's a problem. Everything here are problems to be solved. The techniques to actually make these interconnects, which is where we now expect the higher problems, you can do wire bond. Wire bonding up to 100, beyond 100 is challenging, because actually the wire, it's an inductance, and it increases the losses. And if you need a pad of the size of your bonding tool, that's a capacitor, and that will limit the frequency response. So people commonly use flip chip, and on the flip chip, the problem is that you need to put these bump balls here, which actually have introduce electrical limitations. And of course, when you have different materials, then you can have thermal issues if you have a component that basically is a heater. The frequencies that have been used up to 250, these technologies are okay, but if we want to push this higher, it starts being challenging. And what we are actually introducing, and technologies that we will provide solutions to process, solutions to process these interfaces, is with additive manufacturing. Additive manufacturing of the substrates to adapt it to the size of the different chips that you want to put together, and additive manufacturing of the interfaces. There are different technologies that we expect that companies will not want to invest in having the equipment, because they will have to develop a process before they buy the machine. So we are going to be the place where the different technologies can be tested. There are technologies like ultra-precise deposition, jet ink. There are many technologies that we aim at least to be able to provide consulting and hopefully equipment where companies can develop this process and test them before they buy any equipment. And we are also bringing in a new technology, thinking out of the box. Actually, this came from a European project, Pathfinder project that we coordinated. These interfaces, actually, the dilemma that we have closing up chips together, because we need to shorten, decrease the losses between components in microstrip lines, but we need to space them apart if they have different thermal requirements. We actually develop an interface that allows you to interconnect at high frequency without the power penalty, without the losses. This is with the electric waveguides. We've processed this on deep reactive ion etching, and we are able to develop these structures, basically what you see as a standalone or within part of a larger structure that incorporates other elements. And with this, we have losses that are actually matching those of the lowest optical waveguides. And this is for the electrical. So now we have a solution to interconnect the high frequency devices without the losses of transmission lines. And you don't have to define your architecture by the losses of your interface. Now we have, is sort of the waveguide, the fiber for the RF. And with this, we also avoid problems of current interfaces. This is actually a picture of a transition that we have in our lab. So this comes out of the manufacturers and basically allows us to interconnect devices and has a bandwidth that we have measured beyond 400 gigahertz. Actually, we interconnected, well, the question was how we integrate this. And we've partnered with colleagues that are actually developing high frequency devices, photodiodes, with Duisburg Essen. They have a modified UTC structure, and they were able to integrate the launcher. You can actually see here the electric waveguide. And we compare the electric waveguide with the standard GSG probes that are common in the industry today. And we were able to demonstrate that actually you can have a single interface that connects high frequencies over the whole frequency range that you could not cover but changing the probes. And changing the probes means that you have to leave this probe and land another one. And this is a very tedious process that usually is being done manually by experts, especially if you move in the higher frequency range. With this interface that we are going to put in this, we are going to introduce in this pilot line, we are going to sort of provide a new type of interface. We've done this also with standard GSG components that we flip chip, and we have succeeded in getting results out of this. And actually, this technology is what we aim to do is basically to develop these interfaces going from the fiber comfortable distance, going down to the chip to be able to provide these interfaces as compact and low-cost RF interfaces that we have aiming to make this a standard in a new standard in the industry. And just to finish this, you can actually already find this commercially with a spin-off from our university, in which you can actually find this. This is a high-speed photodiode with a single interface beyond 600 gigahertz. This is basically to demonstrate that this interface is actually high frequency, is guided, and you have all sets of interconnections that allow you to connect backward connected with coax and rectangular waveguide, making this one additional interface that the RF industry can now interface the high frequency components that Photonics is producing. And with this, we will be able to move data much faster in our components, because this is basically not just it's actually intended to make it reduce the distance down to chip-to-chip interfaces. Thank you very much.
Thank you very much, Guillermo. Any questions from the audience? It's time for questions.
Hello, thank you very much for the talk. I'm Steven Martinussen from Epiphany Design. I'm wondering about the future of these probes in packaging applications. specifically if there are any limitations on the density relative to conventional wire bonds. If I needed, for example, an array of 16 of these 16 channels on a PIC, how closely would I be able to space them?
Yeah, that's part of the figure of merit. It will depend on how fast you need your interface to go. Because every time we know that engineering, nothing is for free, and everything comes with a cost. So if you can work with the frequency limitation of wire bonds are going to stay. That's not the interfaces we are aiming to replace. But the interfaces that you need in high-speed modulators, and that also will depend on the density that you can integrate the modulators with, is the interface that we want to replace. Or from serializer, deserializer, and the optical modulator. Those interfaces that the wire bond will not do, because if you need to go to higher than 100 gigahertz, and actually that's the trend. The trend is that the electrical single channels are reaching the 100 gigahertz today, and what is expected for the future is even higher frequencies. And those wire bonds are not the solution. So those are the solutions. And then the distance. What is the distance that you want to space those two components? If you need more than a millimeter, then probably you will need this interface. And the density is something that we're still working around because we have not explored the limitations of how narrow, how small you can make these waveguides. The smaller you make them, the higher the frequency they can carry on, but of course you press on the lower frequencies. And that's why it's part of the research that is involved in the pilot line. Thank you very much.
Thank you too.
Thank you, Guillermo. Okay, thank you very much. Let's move to our next speaker, to our next talk. Thank you. Now we have with us Francisco Díaz from the University of Vigo, who will present their participation in PICS Europe. Thank you, Francisco.
Well, good morning. Thank you very much once again for inviting me to participate in the 8th Photonic Integration Week. And thank you for hosting this event yearly, Pascual and Gloria. Well, I'm going to explain a bit our participation in PICS Europe and emphasizing again what all the previous speakers mentioned. So, first of all, I am going to explain a bit who we are and where we are. So we are a small group dedicated to integrated photonics since 2017. So we are in the University of Vigo, northwest part of Spain. So we're a really small group, but we've been growing since the last 5 years. So we have an infrastructure dedicated to simulation and testing in the TextBiz, a business park located in the university campus. And our motivation is to develop, because we are engineers, we want to develop IP to be licensed to companies or creating university spin-offs. So the idea is to provide also services on demand for companies in terms of design or simulation or characterization and training. So we have 2 small labs. One is a showroom, is more for dissemination and communication, because although all of you are experts in the field, nobody knows, still right now, nobody knows what is integrated photonics. So we want to explain to high school students or university people, also politicians, what is integrated photonics and what it's useful for. So the idea is also that we have a lab dedicated to design characterization. We also have a small wire bonding facility. In the same building, we have a proof station with automatic and with remote access to all our researchers and trainees. And we also give here some events or host some events and give training schools. So right now we have 6 people dedicated to, well, these are in the right side of this slide, you can see the research areas. We are doing sensing and communications mainly. Also, we will, with this pilot line, host a big infrastructure dedicated to packaging. But we have in communications and sensing 6 people that works in the optical, classical or quantum communication, and also new materials for connectivity. In the packaging R&D, we'll have 15 people working on this new infrastructure. So our focus is in 3-5. We don't work with silicon. We work on mainly indium phosphide and gallium nitride. And the idea is to do from design to simulation and also low frequency testing. So this is how we are, what is the organization of the lab. So we have also people dedicated to project and administration support that is not mentioned here. And in overall, we are around 26 people. So right now we are currently working on different projects. One is this one, Retina. We are working on developing a LiDAR for robotics. Mainly, this is a fully integrated FMCW LiDAR based on indium phosphide and also on indium gallium arsenide and quantum dots snapshot spectral images. So this is a project that will end in 2026. We also are coordinating and running microwave photonics for space. It's a project with 15, it's a Marie Curie doctoral network with 15 students and 11 partners in Europe, covering from the design till the packaging of all the devices needed to have microwave photonics currently running in a satellite from the communication and sensing point of view. So all different devices will be designed, fabricated, tested by these 15 doctoral candidates. This project will end in 2027. And at the same time, we are working in the Spanish R&D and training Cátedras chip. This project, from our point of view, has a double goal. One is to train 20 people yearly during 3 years in all across the value chain. So the idea is that they will be receiving these 7 modules that you have here. Actually, this started, the first edition started in January. Well, last week of January, first week of February too. So first, design and testing of PICs, both passive and active devices, testing of RF integrated circuits. Also, they will receive training in clean room fabrication. They will be sent, because we don't have a clean room in Vigo right now, they will be sent to the INL in Braga. So they will be receiving clean room fabrication, packaging of photonic integrated circuits, quantum technologies, and also transferable skills for all the trainees. So we have some industrial partners, also companies that are involved, but also other RTOs, like some of them are here, like DataTech, but also ICFO, IMEN, it's a technological center in Vigo, Tyndall Institute, Keysight, and all the people that are giving these trainings are well known from IMEC, Ghent, Tyndall. So the people will receive, we think that are giving the best training that we can give to people that have an overall knowledge all across the value chain. So there are also some specific trainings that will be given later for people that want to be specialized on some of these modules. At the same time, this project has also a R&D side, because we want to introduce the test design kit concept. So what we want is to develop a wafer level testing tool that can be agnostic from the technology. So we can test different wafers coming from different technologies with different temperatures, powers, ranging up from 400 to 1,700 nanometers. So in the future, what we want to move in two different directions. One is for packaging, of course, but the other, this is the motivation for the talk today. But also we want to move in what we think could be the future of connectivity and mobility solutions in gallium nitride on silicon and also in indium phosphide on silicon. So so we want to measure gallium nitride on silicon technology and indium phosphide on silicon technology that are in a level of maturity that can be in a TRL that can go further to TRL 7 or 8, and then go to high volume production. And this is where we are located. This is a slide that I want to give thanks again to Pascual, because this slide has been moving from different presentations yearly. And this is a picture of the Spanish ecosystem, and this is where we are located inside the Spanish ecosystem. Mainly, of course, being an RTO, we designed a small facility for testing and now moving to packaging, always from the R&D point of view. So, where we are in PIX Europe? Well, as Valerio said before, and also Guillermo, Joaquin, everybody is speaking about this, PIX Europe wants to create the first integrated open access pilot line. I think grouping, and also distributed. I think this could be the first one in the world dedicated to PICs. Open access, distributed across Europe, with some different objectives. One is to establish this first open access ecosystem, develop and standardize breakthrough technologies related to PIC processes and in different technologies, offer also advanced services in different technologies, in all these different technologies, setting up a seed to increase European capacity in PIC production, also group and foster the European PIC community, because with this distributed pilot line, the idea is to have a big interaction between all partners that right now are concentrated on their topics and isolated, let's say, in different countries. Also establish training and dissemination programs, grouping together all the different projects related to training that are being given now, JPICs, Spanish cátedras, different projects that for training that different countries have in their own roadmap, and also collaborate with other European and national semiconductor initiatives. So we participate in PICS Europe in these three work packages. One is related to design and modeling, the other one to PIC packaging, and in PIC testing. So this is where our lab is also being concentrates its capacities. So the PIC design and modeling work package is dedicated to compact models with predictive capabilities. So the idea is to develop these compact models using a common methodology. This is something, as also Joaquin mentioned before. The idea is that if you have different technologies and then you are going to develop different PDKs, but the methodology should be common for all of us, so we can establish these connections. And we are going to be task leader of this 4.5 task. That is the creation of a measurement-driven model. I'm going to explain it right now. The Work Package 7 is related to packaging, and we want to, this is something that could be, I think this is the motivation for us is to develop, you know that the cost of the PIC is also driven by the cost of the package mainly. So the idea is to develop a cost-effective package with new materials. So that can be produced in volume, could be reliable, could have short process times also. So this is the idea of this work package. And we will be leader of this task 7.5 that is called packaging materials that we will see now. And finally, peak testing. The idea is that we will define test protocols and also methods for high volume manufacturing. So the idea is to optimize test, inspection, and reliability, and make automation and methods for this high volume manufacturing. So in Work Package 4, and this is of course for this part or hosting site of PIX Europe, we are going to move to this new facility that you can see on the right-hand side in this picture here. That will be available from September this year. So the idea is that we will move all of our two labs that we have now to this new facility at the end of this year. So everything will be hosted there in a lab that will have around 1,200 square meters. So we want to provide statistically device models, also accurate device models, coming from previously data, coming from measurements. So the simulated performance of the demonstrators that we will receive can match the final measured performance with some statistical variations, of course, coming from fabrication. So we will receive different demonstrators, like the ones that University Carlos III or CNN can give us. So we will provide device models coming from these demonstrators. So we will standardize device models of the building blocks across from 400 nanometers to 1,700 nanometers. Also the routines of peak measurement. We will standardize design kit data formats. So it could be agnostic to different software vendors. So the idea is to isolate these data formats from the software, from the commercial software. And also we will develop design kits that will include this statistical measurement data. In the packaging, in Work Package 7, the idea for the packaging is to, as I said, to provide cost-effective packaging materials. So we will be concentrated in some of these materials that you can see here. So we will use 3D printing processes. So we will incorporate high reliability materials, for instance, liquid crystal polymers, PEK. So thermoplastic, for instance, different variety of PEK materials. Also alloys of different metals and metals themselves, and also aluminum oxide and aluminum nitride materials. And then finally, we will have fully packaged demonstrators to validate the performance of these packaged materials and designs, with the idea to be transferred to volume production. But the main goal is that they can be reliable, cost-effective, short-time processing, and scalable to high-volume production. And finally, for peak testing, the idea is that we will implement new on-wafer electronic photonic test methods. for different wavelength ranges, like for 400 nanometers to 1,700 nanometers with different temperatures and different powers. So the idea is that this wafer level testing method and protocol can receive different wafers with different technologies, but can be adapted to do this for these different working conditions. So we will also translate these characterization methods to high test environments, to high throughput test environments. So this can be done massively. And then we will also develop test and methods both for front-end and back-end production and strategies to scale up to high-volume production. And I've been fast, I think, but this is the end. Thank you very much for your attention.
Thank you very much, Francisco. Any questions from the audience?
I think it's the first time that that the session ends before the end of the session.
We are just on time. That's perfect.
¿Eh? Ah, fantástico. Bueno, entonces, then I am on time.
Hola, ¿qué tal? Víctor Sergio de New Quantum de Cambridge. ¿Podrías hablar un poquito más de los detalles de las cátedras que dan acerca de los diferentes paquetes? Oh, sorry.
Sí.
Could you
Sure, yes, sure. Well, these cathedrals for us, because it depends on each university. This project has been awarded by SET. So depending on the university, the training is different. So we focus in the University of Vigo on giving a training with different modules with a specialization title given by the University of Vigo that has also micro-credentials, so you can have your ECTSs and take these ECTSs with you. So the idea is that we will have 3 different modules in overall seven trainings. If you receive these 7 trainings, you will be awarded this title of a specialist in integrated photonics design and testing technologies from the University of Vigo. So these trainings, depending on the module, can be from 2 to 3 weeks, and in total is 5 months. Right now we are in the second one. We've been given RF, passive, and now we will start active devices, and then all the students will move to INL in Braga and will be there for 3 weeks for clean room fabrication training. And then they will come back to Vigo and will be, of course, it's in person. It's not because it's difficult to give. But the idea is that we are recording some of these sessions, the theoretical ones, so they can be given later on demand if someone wants to.
So potentially we can send some people to go through this
sure.
training,
Sure.
come back to us with a...
Yeah, sure. There are 20 people per year because we don't have, it's small, so we don't have capabilities to give this training to 100 people. But for this year, we receive 35, nearly 35 and 40 CVs of people, so there is a selection committee, but initially it's fully open, so you can send it, sure.
Thank you very
and
much.
It's for free.
Free?
Yeah.
You'll hear from me.
Yeah. It's an important point, yes.
Oh, excellent. Thank you very much.
There is a compromise that you must attend in person and receive all the trainings. If you are not attending percentage of these sessions, another one will enter.
Gracias.
Hi, this is Peter from Lucida Photonics. I was wondering, for the testing facility services, will it also be possible to test chips that were not made by PIX Europe?
Sure.
Okay. Because that might be interesting for us, for instance, to depending on the capabilities of different labs or companies.
No, sure. The idea is that this is an open access facility. So it has 5 years of research and then plus 5 years of sustainability. And in this sense, for instance, we are working right now on the sustainability side. So we want to strengthen the relation with companies dedicated to packaging, but also to testing, to have these facilities open. Yes.
Looking forward to collaborate.
Okay. So we can talk later. So.
Okay, thank you very much. Let's thanks Francisco again. We need to move on to the next talk. Thank you, Francisco.
Thank you very much.
Okay, so we will finish this session with Pascual Muñoz talking about the hybrid photonic chips on the pilot line in the PIX Europe.
Thank you, Gloria, for the introduction. Okay, so we're closing this session with my talk. It should be the second, but I've been a little bit busy with the team trying to see how we fit you now and over lunch. Everything is more or less solved, so don't worry about that. Okay, so I will describe briefly which are our activities on the PIX Europe pilot line. But first of all, I will give some context, talk a little bit about us, then the activities and a conclusion. So we are working in UPV Fab, which is a small pilot line actually inside the university campus that was established in the 2010s or so by a local company called Silicon Energy. It was their pilot line for manufacturing their solar cells. Then after that business didn't go well, as many others for the solar market in Europe. The clean room was restarted for a sensor project by, again, a local company, then Austrian Microsystems, till 2018. But by that time, so that sensor project didn't have continuity, so we proposed to the rectoral team to give this facility another opportunity. And then we team up with different research institutes. We are from the Telecom Engineering Institute. Actually, we do photonics. And then there are other institutes doing electronics and chemical engineering that we share, like the common need of a clean space, working on mostly silicon substrates, should we say. But not only that, we designed a resident program for companies, so a resident company program. And we have engaged a few companies. Most of them, they are engaged in that program. You will be visiting later this afternoon the clean room. So there is a tour from 5 to 7 p.m. So just be on the meeting point over there. But in very short, I can say it's 2 areas, a white and a yellow room, more or less above 200 meters square each. And we have equipment for the different areas you will see later. And we do also have a photonic testing laboratory in this same building area that you will be also visiting. So we've been working in photonics and photonic integration, actually in photonic integration since 2004, 2005. From our activity, we founded the VLC Photonic that was later acquired by Hitachi. And we have been focusing recently, since we dare to dive into manufacturing. So technologies like silicon nitride within UPV fab and 3.5 semiconductors that at present it's externalized. And we're hoping that many others many other facilities are opening up, maybe in Vigo, France soon, with the Spark Foundry. But currently we're sourcing the 3.5 externally. We have been working for different application areas with different companies. And we are developing our hybrid integration technology based on transfer printing. Our mission is to establish this platform. I will be totally honest, and you guys working in technology know with this 2025, we have been pushing it like it was 2023, it was 2024, but now it's 2025 to establish our technology. We're very close. In the meantime, by December 2022, we already had sort of idea of a business plan for this, even before the technology. And we started with that, and we actually incorporated hybrid photonic chips, high-peak, last January. So this company is the one where we want to transfer the commercial exploitation of the technology. So actually we have licensed the IP that we have registered so far. And it's a company that should enable several verticals with a technology platform. At the beginning, we don't want to do, foundry services or open foundry, rather more contract manufacturing for third parties. This is all done in the context of PERTE-CHIP, which is this flagship program for semiconductors in Spain. I think that several of the previous speakers have mentioned the different action lines there. Mostly Cátedras chip, which should maybe be transferred by industrial chairs. So our co-sponsor programs by industry and public funds. And we have one in the university, which is a PIC UPV chair. And PIC UPV chair is participated by 5 companies along the supply chain. So Spark Foundry, VLC Photonics, and Ipronics, or Material LiDAR, and CalSense. And we have one part of the program is research, so we are educating through research, so postdoctoral personnel and PhD students. But one of the strongest actions is the master. We are currently running the 2nd edition. We have already finished the 1st edition in January. And we also have a trainee program for student internships in the facility. So far, since September, we have involved, I would say, around 50 people already. I don't know the numbers exactly, but around 50 people, combining the people being in the research area and the people in the research activity and people being in the education and workforce development activities. And as Fran mentioned, the monies from the ministry allows us to subsidize the master in full. In fact, we don't charge students for the master. Not only that, in Valencia, we pay them for studying. So I think that they are so far quite happy, despite, starting over was a little bit fast, and you always find some difficulties and challenges when you need to start very fast. So that is the context. So in PICS Europe, and I think that you've seen many similar to these slides before, so I will be very brief. In PICS Europe, we were chartered to coordinate a work package on hybrid photonic integration. We will aim to be the lead node for this in the project, and to incubate technologies and end users around the hybrid PICs. We get funding, as you may know, probably other speakers and Valerio mentioned. This is a project subsidized 50% by CHIPS EU, so European money, and then the other 50% by the member states. But our university also decided to invest with a new location and clean room. We are starting up in UPV Fab, so the facility you will visit this afternoon. But we have recognized that we need, first of all, more space, second of all, a proper area for the type of activity that we want to do. We have a 5-year program. I think probably Valerio said it, and a compromise to be running it for a few years more in a self-sustained mode. This one, Valeria showed it, I saw it at the very beginning, which shows the technical activities with the core technologies, the design, the packaging, hybrid integration, and a combination with electronic technologies. So we are involved with several partners. I think that probably there are a few missing there, so it is ICFO, CNM, Warsaw University of Technology, Silicon Austria Lab, UGent, but there is also CLETI, there is IMEC, there is the University of Ghent, so no, it is already there, sorry. So there are also a couple of partners from the UK, University of Cambridge and University of Southampton in the work package. So I won't be as much specific as my previous colleagues, but we try to summarize this in this kind of picture. I acknowledge I draw like a little child, so sorry for that. We didn't have time in August to do a very professional picture when we wrote the program. But I think it's good enough to tell you that we want to combine different type of technologies, mainly onto silicon substrate. So that is to bring onto the silicon substrate, which is, we can acknowledge kind of a winning technology because of the many reasons that you already know, to bring what is missing. And then what is missing in terms not only of optical gain at different bands, as you can see on the left-hand side. So there are activities for RGB optical sources on silicon nitride, and then OC and 2 microns band as well. But not only that, not only gain chips, should we say, but also other materials like the thin film lithium niobate, aluminum nitride, 2D materials, phase change materials. And the means for combinations are various, depending on should we say, the required scalability or the market perspectives or the volume perspectives for the different technologies. So we have, I already mentioned microtransfer printing, that there are, of course, again, IMEC have a strong leadership on that, and we will be also using it in Valencia. But there is also LIFT, which is a technology by TNO, and also some bonding technologies that other partners will use to make the different hybrid platforms. Concerning to us, we will have 3 technical activities, which is a 3.5 over silicon nitride SOA device for the optical C-band. But we also will dare to develop a technology for dye transfer of 3.5s, and the dye then later on be patterned after transferring to the silicon nitride wafer for the O band. And complementary to all of them, we have there as well to put in place a plasma dicing technology. I already mentioned that the university recognized that it is a very key project for their interest. So since we are aiming for pilot manufacturing, this is probably no longer a scientific and technical research facility, what we want to do in. And we also want to have it as a hub where the industries can come and sit around and work in the pilot line and establish nearby. So since the type of activity and the requirements for future growth are something that is probably has not the best fit on the campus, the university, together with us, is looking for, actually is considering a few locations nearby Valencia, where we can grow. So we aim to start to have a facility of 3,000 meters square with a clean room of 1,000 meters squares. In terms of equipment, PIX Europe will fund us to incorporate 53 pieces of equipment for front-end and back-end processing, as well as for characterizations. In very short terms, we should be able to process with that equipment 3.5 wafers up to 4-inch and silicon wafers up to 8-inch. And the capital equipment will go mainly to the usual suspect area. So I should have put lithography before, but litho, deposition, and etching is gonna be getting most of the funds from the CHIPS JU. and the member state. And then, of course, since we do photonics, we will also equip ourselves with photonic and optoelectronic characterization equipment. Okay, teams, but in the sense of people. So we already have a large group of people working on photonics and photonic integration technologies, also diving into manufacturing since a few years ago. So some of the positions that we need to cover for this particular UPV project are already covered, but we're looking for people in the technical and operation and business part of the story. So, I mean, this will be available. I can make it available to you. We are discussing already with a good number of people. A good number of people is already appointed, and but we still need to look for more. So please let us know if you are interested. We will be happy to discuss with you. And last but not least, also ChipsJU, in the same call of the pilot lines actually, they launched a call for competence centers that should be like the bridge between the end users and the pilot lines. In Spain, we have for photonics PIX Spain Competence Center. In this case, UPV will be coordinating this competence center. And as I mentioned, it should be the bridge for the, in this case, mainly the photonics pilot line. And tomorrow morning, we have a representation of different competence centers, mostly dealing also with photonics. That is the first session for tomorrow morning. Okay, so conclusion is we have been very active and busy building an ecosystem in Valencia. We acknowledge that one of the let's say key elements were these industrial chairs, where public and private organizations invested in educating the future human resources. We have different programs around. We have now the pilot line that needs people and other projects of course in the group, and as well as the competence center. And I trust that we can build a very vivid ecosystem in Valencia that lasts for long, hopefully. So that's all from our side. Thank you very much.
Thank you very much, Pascual. There's a question over there.
Can you hear me? So what type of heterogeneous integration technologies are you looking to implement? I mean, in your center and in the project?
So if I heard well, you're asking about the hybrid integration technologies that we're looking at in the project and in our center in particular. Exactly. Okay, so in the project, it is quite, the variety is quite large, as I tried to capture in a single image when we wrote the program. So there are crystals, there are semiconductors, there are dielectrics. There is a little bit of everything. And I think I said we try to bring to the silicon nitro the things that are missing for different applications.
So what material? I mean, what type of technology? Is it like wafer bonding? Is this
okay?
Like
okay. Yes.
Flip chip.
Yes. I also mentioned that. So I would say there is everything. So yes, sorry for that. I know it's not maybe the very best answer, but for instance, there is the transfer printing that several partners will be using, the micro transfer printing. There is the lift technology by TNO as well, and there are bonding and direct growth as well of things. So depending on the type of activity, as I said, depending on the volume perspectives of markets, we will resort to one or to the others.
And is the envision to be like offered as a service, for example, transfer printing as a service or flip chip as a service, or is it the end platform will be only offered as a service?
Okay. That's a very good question. So the pilot line has to exist alongside with the end users. It doesn't make any sense that we do a technology and then we try to push it to the market. So I think that the pilot line is open to every type of interaction that end users require. So if end users require transfer printing as a service, we should be open to provide transfer printing as a service, for example.
Thank you.
Any other question from the audience? Are you willing to go for the coffee? Okay, so I think we can stop here. Let's thank Pascual.
Thank you. Venimos a las 11:30 o así. Okay, so then we close the session and we will be coming in approximately 25 minutes, 30 minutes, okay? 30 minutes, it's okay.
Okay, welcome back to all of you. I hope you enjoyed the coffee and the break and the conversations and the chats with the people around. And now we are moving to the next session, which is the company pills. This session is focused, or is thought to involve the companies who are working with us as sponsors or either exhibitors. Sorry, because I just realized that we are missing a couple of logos, so I try to include them. That's why you see something rear over there. And well, they will invite you to visit them to visit them on the exhibition, and they will give you some lights, the main points of their production on the services they have. Okay, so the first, I must say that I've been struggling them a little bit to fit the presentation on time and the slides. So thank you very much to all the presenters for your collaboration on that. And well, I hope that that helps in order to be quite dynamic on time, okay? So the first presenter is Alberto Hinojosa from VLC Photonics, and the audience is all yours.
Thank you so much. Thanks everyone for being here. I can see that this room is very packed, so thanks for being here. And today I'll present the latest capabilities of VLC Photonics on backend testing, meant to cover the reliability and scalability of PICs, offering a cost-effective solution. So before that, I'd like to bring your attention to the impressive growth of VLC Photonics over the last 10 years, moving from a startup from this university to become one of the key players in the photonic industry, consolidating how a design and test house is a fundamental player to connect the technology and the end users. For those who may not know, VLC offers end-to-end engineering solutions, services, specializing in design and testing, and we engage with customers either in individual stages, or customers can entrust us for the full cycle development, from prototyping to pilot production. And if needed, we count with our Hitachi partner to scale up on volume. On this line, based on the undoubtable investment of Hitachi to expand our backend capabilities, we are glad to announce that we plan to move to a new facility very soon, in a couple of months, where we will have our own clean room, which will be designed to accommodate all the new equipment. This is a very exciting moment for us, since it positions ourselves, so it reinforces our position in the photonic ecosystem, mostly to meet the demands of next generation of PICs. And I'd like to make a break here. Probably more of you are aware that the expected annual growth of silicon photonics is about 36% annual growth. And there are traditional applications which are demanding more performances in terms of high speed, power consumption, and parallelization or number of channels. Together with that, there are new players and new applications, like in photonic computing and quantum applications. At the same time, new applications are emerging, trying to promise high performances to overcome these demands. So we have seen already the plans to hybridize, integrate different platforms and materials. So overall, we strongly believe that the new capabilities on the backend testing will serve to address the challenges on scalability and reliability in a cost-effective way. So when it comes to backend testing, we take a forward-thinking approach, while maintaining the front-end design development perspective, meaning that we try to combine design and testing on the each iteration. So I would like to count 5 different new capabilities, key capabilities, that will be available on 2025 from VLC Photonics. First of all, automation in optical and electrical proving. This is essential to obtain precise, accurate, and massive data in a repeatable way to get the statistics that allow to feedback on the design and development of circuits. We will count with 2 wafer level testers, also a 1 die level tester, and another die level tester with automated pick and place. All that will reinforce our capabilities to cover the demand, the needs of customers on getting these statistics. We also have die sorting to move dies from blue tape to gel pack. And this is quite interesting for many customers as well. Second, we come with an extensive instrumentation from the electrical and optical domain, covering from the visible range, ultraviolet, up to mid-infrared. Specifically for datacom and telecom, we come with some Samtec tools which allow down to 0.1 picometer resolution on the O and C band. And this is quite interesting. But not only that, we also come with lunar reflectometers for optical backend scattering measurements. Third is the high-speed signal. So when it comes to communications, now we are seeing the demand on the high speed. So we have a Keysight late with component analyzer, being able to measure up to 110 gigahertz on 1550 nanometers and 1310 nanometers. But not only that, we also have another kit for bit error rate analyzers, specifically a arbitrary waveform generator and a real-time oscilloscope that can measure up to 112 gigabaud for amplitude modulation formats. Fourth is on the thermal and humidity reliability. This is crucial to validate the reliability and functionality of the circuits. So we count with some climatic chambers which allow for a range of temperature down minus 80 degrees up to 180 degrees. And we can control the relative humidity from 5% up to 97%. Not only that, but also we can do the electrical biasing monitoring of the photonic circuits or the circuits itself at bare die using some customized proofs, or we can do electrical and optical monitoring with packaged devices. So with this instrumentation, with this equipment, we can cover quite a lot of the standards and certifications on the electronics and automotive industry. So through our network of Hitachi, which is a leading company on imaging instrumentation and visual analysis, we have access for root cause analysis of inspection of those dies, for scanning electron microscopes, and scanning defects X-ray, and also focus ion beam. So with all that, we can expand and cover not only the reliability test, but also the inspection of the failure mode analysis. And all this operated in a ISO 6 clean room right now in the UPV with full ESD protection. Finally, we have very basic capabilities for test assemblies, and this is essential to combine either for the high-speed signal or the reliability test. So we have the tools to do wire bonding, also ribbon bonding, flip chip, and edge coupling of fibers in a different approach. So using epoxy or free epoxy for high power coupling applications. So all on it, we like, our aim is to link the equipment to our expertise in order to address the needs of the customers, which basically is sorting out the no-good dies and evaluate the manufacturing yield variations. So just to finish, I would like just hold up your hand. So each finger will be one of those capabilities. And now, if you close, you have a handful of services at your reach that you can use. So what is next? We have it clear. We believe on open our hands to be ready to open to collaborations together. So please don't hesitate to contact us. Thank you so much.
Thank you very much. Thank you very much, Alberto. If you have some questions, we need to move on. But you can visit them on the exhibition, not on the exhibition, sorry, but Alberto will be with us, and also David and Inigo will be around, so please go ahead and annoy them a little bit. No, I'm joking. So next speakers, our colleague from FineTech. Thank you very much.
Hello. It's good to have you there. It's good to be there. I was there last year already, and that's, I found that the Spanish ecosystem is quite booming and interesting. You have all the different steps from R&D labs, startups, design house, investors also. So that's probably a good place to be for the next 5 to 10 years. Not speaking about Spain, it is a good place. I will speak about FineTech. So I'm Sylvain Dulfi, and let's see who is FineTech. We are submicron die bonder manufacturer, so we build machines. We've been doing that for 3 years, 30 years, maybe 33 if I go right to the details. From tabletop machines to automatic machines, we are focused on what we do, and we only do that. We don't do other things than die bonding, which means that we have some expertise in this subject. We are a family-owned company based in Berlin with a presence worldwide with different facilities in the US, China, Japan, and Thailand. What we also have is not only we fabricate, manufacture those equipment, but we propose the process support going with it. Part of the discussion we have with, let's say, half of our customers is that the design picks, the design chips, and they want to have a product. But to have a product, they need these, I don't know, wave guides, laser source, photodiodes, package, and to put that together one way or another, whether package or just on the wafer. And this part is often not forgotten, but taken after the design. And it's always pushing some limits, pushing some also interest there. I went to different conferences where globally in semiconductor, the packaging is 15% of the cost. Stabilized semiconductor part. For photonics, it's 50%, probably more today as there's no standard. So we aim with our machine to propose you the ability to do whatever you think is good. You are the one to design, we are not. But we propose the machine to do what you think about. And our motto is bringing vision to life. As a German family-owned company, we try to verticalize everything to control what we do. So we develop the hardware, we develop the software, which is very important. When you buy an equipment, you then discover that from one piece of equipment to another, maybe the easy-to-use thing is very important depending on who is using it. And if you have several users, if you don't use it every day, sometimes you lose the way of doing tricks. It seems, according to our customers, that our software and our interface is a good one. Of course, global service due to the worldwide presence, and process, as I was speaking about, and I will go in the detail to this part, because finally that's where things happen. You don't care about buying a machine, a big one or a small one. You care about having a bonding, a flip chip bonding, a die bonding, a gluing, etc. our portfolio, so from tabletops up to full automatic machines, they can all be used manually for R&D purposes, for process development purposes, but also for production. We use the same software for all the machines, from tabletop to automatic machine. So yes, we work also in this part of lab to fab thing. You can develop a process on a tabletop machine and then put that on an automatic machine in another place worldwide. It happens more than I like. I wish that all the production stays in Europe. Nevertheless, some machine goes to Mexico, to the US, to China, Southeast Asia, whatever. So what we focus on, of course, is accuracy, die bonding. You're going to integration. There was a, I'm not, okay. So there's integration, and as we saw this morning, the interface between the different fast chips and the fiber optics is always an issue. So you have to design something that is closer, that is going faster, and we can help place those things very accurately. We call our tabletop semi-automatic machine because all the process part, all the process parameters, whether it is glue dispense, whether it is thermocompression, whether it is heat, soldering, whatever, all these things are fully controlled by the machine, even on the tabletops. The only thing that you do is the alignment. You do it manually thanks to the video, and you know that with video we can do whatever is possible today, and probably a lot more that you can see. And of course, the automatic machine can target production. I said that in introduction that we focus on what is our core market. Our core market is not the 10 millions a year product. We will not go to that. We propose platforms that are modular, where you can have several processes in the same machine. So you think of a module where you have two different glues, where you have one soldering, one thermocompression. You don't have to reconfigure the machine. The thing is just being done in the same machine. You just pick the right modules that you want when you buy the machine. Life is life. Afterwards, you change the design and you want a new module. Okay, it's a 2 hours retrofit. Every module is a 2-hour retrofit. It's something very easy to upgrade. You can ask the previous presenter. They have one of our tabletop machine, and the upgrade was done last week. And so the second part, as I told before, very important one is technologies, bonding technologies for us. How to help you on that, how to make those bondings happen in the machine, and of course the end application. Almost everything's possible except the wire bonding. We don't do wire bonding. All the rest is, yeah, you can target it. What I see in advanced R&D, in photonics, in heterogeneous, hybrid, whatever the name you, you have for that, what I see coming now is laser soldering. So having a laser doing the solder in less than 1 second for a VCSEL, for example, through a wafer. So die to wafer, through the wafer. It has huge advantage of being fast. It's not moving. The die is not moving during the process. And yeah. And there's also another advantage is that there's no thermal coefficient on 3.5 on silicon, for example, where they move, and then the accuracy of I don't know, the bumps or the pads or the copper pillars is being wasted. So those things are coming in, already existing at some of our partners, and things that should be developed in the next coming year if I look at the incoming orders with machine with laser. Indium is also one thing, so that's part of the thing that is very tricky to target doing the bonding because it's small, because it's soft. So it moves a lot, but we have some confidence and good work on those topics. There are some others, other application and techniques, so just come by, I'm down there, and we can discuss on those. Thank you.
Thank you, Steven. I told you. I'm pushing too much, but we are quite a lot. Sorry. Thank you. Thank you, Sylvain. Thank you for your presentation. So the next speaker is from Fibercom.
Okay, so this works, I hope. Okay, good morning, everyone, and buenos dias. Thank you very much for having us here, to the organizers, and I'm gonna try to be quick, okay? And thank you to Fabercom as well, and I work with Expo, and Fabercom represents Expo in everything that has to do with photonics, okay? I'm going to be talking about Expo and how Expo comes into the whole picture when we're talking about PICs. Okay, so let's see if this works. Okay, just to talk really quick about Expo first. For those that are not familiar with us, we are a Canadian company. This year we are celebrating 40 years in the industry. And we are quite happy with that. We take a lot of pride in our history, and we were born, as I mentioned, in Canada, in Quebec City, and we take pride on anything that has to do with innovation, engineering. We have grown through different acquisitions, and 7 years ago, Expo acquired Genista, a company in France. It might ring a bell to some of you. And then just 2-3 years ago, Expo acquired a company in Quebec City that is called EVA. And Genista portfolio had advanced instruments for optical testing. And then EVA, what brought to Expo was everything related to peak testing. Okay, so this is at a high level what Expo is. And talking about the peak testing, EVA and with Genista, we have a large team of scientists and also quite visionary entrepreneurs that have designed different solutions to characterize peak. You have seen this through Valerio, through Francisco, and the other speakers, but this is more or less what we are all witnessing in terms of the life cycle of a PIC, okay? From the very design and the foundry, and which is the welfare part, and then going into becoming something that might potentially become a usable device. We've been talking about non-good dyes. This is a key parameter, okay? Because obviously at the moment, as the industry is growing and evolving, this is still something quite important to characterize and understand. And then you have the sub-assembly in the module, because eventually you want the PICs to become a product for end users. The whole point is that Fabercom Expo, we fit on the different stages of the life cycle of a PIC. And we have, our team, our scientists that design our solution, they, in the 3 years, they found out the challenges that are faced through the different stages. And definitely the coupling of the optical heads, the electrical heads is quite an important challenge. And this is something that we have designed our probe station in a way that it can be automated. You can have the GTS into it, and then the probe will go and automate the staging of the die, and being able to do edge coupling, surface coupling, even trench coupling. The other part is the actual tests, okay? And this is one of the critical points. We have heard plenty of times about reliability. Repeatability hasn't been mentioned, but that one is key because you need to make sure that what you do is consistent, is coherent, is always going to be the same way, okay? You want to make sure that it's efficient, okay? Time is of the essence, okay? And that's where we really focus on efficiencies. And the last point is the data management, because data is precious, okay? Data is what is driving most of what we're doing. I think I'm getting to my point. Thank you, Gloria. But the bottlenecks that you see today, this is what we are trying to tackle, and definitely being able to have a reliable tool that is going to be able to characterize peaks at the speed that it really makes sense for going to go into the fabrication. And that brings together the whole ecosystem, okay, of the test instruments from Expo, apart from our probe station. So just here really quick to mention, I'm not going to go through all the different parts of our portfolio, so I'm going to spare you that part. And but we have a booth downstairs. We'll be really pleased to talking to you. And just for those that will be lucky to go to OFC, we're going to have our probe station in California at OFC. So you are all welcome if you can go to California. We're going to have one of our probe stations. We're going to have a live demo so you can see. And what we just want to do is rather than having to do manual work or having to spending 2 years resources and developing something from scratch, and this is what we are doing, and we have a solution already there. So if there is any question, Jorge is there, I am there. We'll be really pleased to talking to you. And yeah, so questions? No questions now? No. No. I was really quick. What's tonight? Yeah, 5 minutes. Yeah, 6 minutes. Okay. Anyways, all right.
I stopped
okay.
it.
Yeah. Okay. Yeah, stop it. Okay. Thank you very much. Cheers.
Thank you. Thank you very much. So the next speaker is from SMA.
Yes, hello. SMA is a small distribution company that was in Spain since 1992. Okay. This comes from a company, French company, was Microcontrol and SET in France. And this company makes equipment for interferometry, laser engraving, for also microelectronics. When the company shut down, we follow the service on the different equipments they have, and we design some special equipments also for different companies, including at the time AT&T, which we sell equipment in Tres Cantos and in USA also. We have done for infrared detector application, some pick-and-place equipment. We have done some testing for very high temperature, up to 350 degrees. The idea was to do equipments on demand of the companies. Of course, not too complicated equipments, but according to customer needs. And this we have done. And of course, we distribute mainly actually is SUS and SET. These are the main. We can follow here, you have an idea of what are the main line of equipments. SUS, I suppose you know SUS, most of you, they are mask aligners. What I will tell about mask aligners, that normally SUS has manual equipments, but the idea is to go to semi-automatic equipments, and then from these semi-automatic equipments, you can, once you have defined your process, you can directly go to a production equipment, because the module are the same integrated in the production equipment. So in SUS you have the mask aligner, which is the main line of SUS, which is maybe #1 on the world. After that you have coater developer. It's the same. You have a very small manual coater. You have semi-automatic coaters where you can develop your process. And finally you can go to a production coater and developer. They have also a line of inkjet printer. We have sold here in Valencia and in other places, in Granada and many places. Okay, and then the next step is a bonder. SUS has bonders for wafer bonders. In that wafer to wafer, this is important in some application, more in optoelectronics, and this also can go to fully automatic bonder wafer to wafer. No? In SAT, we have the lines of flip chip bonder. SAT produce flip chip bonders. I would say that they are in the level of top application. For example, for detector that needs a very large surface with many infrared or vision detectors that have a big surface. So you have a small manual, and then you have semi-automatic equipments capable to do large surface up to 4,000 Newton pressure. And these are the most, I would say, accurate and powerful that exist, and they are also in all places all over the world. In top of that, we have punctually collaborate with other companies like wet benches and ovens for cleaning processes, or with Tepla, and we follow producing when they ask some vibration tables. Okay, I don't know if I am time.
We do have time for one question, if any.
No?
If not,
okay. I am in the expo, so if you want, you can come.
Yeah, you can chat with Segundo. He will be on in the exposition. Thank you in the exhibition. Sorry. Thank you very much, Segundo. So we can move on to the next speaker, who comes from Nanoscribe. Thank you, Alexander. The speaker who is ex-sponsor and exhibitor. Double check. Thank you very much for your support.
And yeah, thank you much for the invitation. And oh yeah, I have. So where is the? Oh, nice. Okay, good. So just a few words at the beginning regarding the company. So we were founded in 2007, are now more than 17 years in business. So we are a German company based spin-off of the Council Institute of Technology, still based there. And so now in the meantime, so what we do is then we sell equipment. So yeah, let's say for a few buzzwords. So we do produce 3D lithography laser systems, so additive manufacturing, and you can do a lot of nice things with that. And so, by the way, so we sold now nearly 400 systems, deliver them worldwide, including also some places then nearby. I'm not sure which one, but then let's press this one. And here are some examples. So, for example, then you can use the technology then for prototyping. So you can print here such a nice element like here surface coupling. So people also produce then here Fresnel lenses, freeform micro optics, spherical lens systems, aspherical lens systems. And so you can do this, of course, then here for mastering. So you can also then use different software and hardware just to do yes, so error-free stitching. And then, so well, what you also can do is then that you can print a smaller stamp. Then, for example, if a step in repeat process, you can just upgrade that to an bigger level, what you see over here. And now, here it's more about what you can do is then here for use the equipment and here for optical coupling. So for example, that some of our customers here, we also were partner in a project where people just here had this grating coupler just to guide the signal out of the plane here upwards, or that you can also print some edge coupling. And the same here then, for example, you can also print here lenses, optical coupling then here on such fibers, fiber arrays, or you can also print here stacked lenses, several level micro optics then to compensate errors of one optical element then with another optical element. So we have quite some patents on that. So we have then, we are the provider. So the system behind, or let's say the technology behind is two-photon polarization. And we are just the company offering the highest degree of freedom, so the highest possibilities then so how do you say, we offer the biggest possibility then to use for different applications. And also then we have some patents here in this field, like that we use directly the resin that is exposed then as immersion media, and also here, for example, then to print on aligned and onto fibers, or for example to compensate then here. So we just use a patent then to compensate here the shadowing effect then for edge coupling. So how does this look like? So the point is then, so challenges then for optical coupling is like, so what you have typically is then that you have some different shapes of mode fields. You have different mode fields diameters. So you see here for fibers, you are in a few micron region, or so for edge chip coupling, so you have as well then here are different sizes, different shapes, and the same here, by the way, so you can always go on an angle with that. So for creating couplers, then of course the same. So yeah, different shape as well. And now just the solution is then to couple these, so to print lenses, then freeform optical elements, then to couple optical elements and out of this fiber arrays, and to couple it into then chips, for example, and as well then here for these creating couplers. And so here you see some examples. So we were partners then in different projects, like so for example, so for OCT coupling elements, or just so for example, and also for the Project Phoenix. And so, of course, this is a very fast overview of different elements. And so, for example, if you would like to see more, then we are downstairs here. Then please visit my booth. Thank you very much.
There is time for one question, still, if any. If not, okay, they will visit you on the exhibition.
Oh, there is a question?
Ah, yeah, of course.
Yeah.
Camille, thank you. Please.
Could you possibly expand a little bit of the different types of vertical coupling that you have?
So it's about then, let's go a little bit back to that one. Or for example, yeah, for this picture then, you see a bit, so this was a project, for example, from Wolfram Pernis Group from University of Münster. And what they did is then, so you see, so if you look from the side at it, then you see that you have something a bit looking like a wedge, and then a lens on top. So and then, of course, here you just guide the signal out then into the, into the other plane. I don't have it here, but for example, there, for example, at the edge, so we also had a project there where we had we printed a mirror where you had total internal reflection, and due to the shape that you adapt the surface, you can improve the output. You can just, how to say it, yeah, the coupling, you reduce the coupling losses then, for example, then like this. And so, yeah, just to give you a few numbers, so typically, for example, from fiber to fiber coupling for green nanometer, we are at coupling losses below 1 dB. And very often here, to print here, these lenses, in-coupling, out-coupling elements, depending on the material that you work with. So with silicon, you are more or less most of the time between 1 to 2 dB, and depending on, I think silicon and nitride is a bit worse. So there you are at 2.5, 2 to 3 dB. And that really depends. So we work a lot on how to increase the throughput, increase the throughput, and how to yeah, increase the output.
Has the surface mirrors or vertical surface mirrors have been the most, the most efficient, or the ones with less losses out of the vertical couplings?
So I think it's easier. So for example, if you can print, there's missing a picture a little bit here. So what we also do is then, if you can print a lens directly on top, of course, then you have a very nice surface. And the point is then here, so you expose with the laser here from the top. So of course, and the laser focus is shaped ellipsoidic. And then of course, yeah, it's a bit more difficult to have at the side, let's say, the good surface, but it still works. So yeah, but let's say to answer your question, yes, it's easier than to have a good output if you print on top compared to the side, but even on the side it works.
You're reaching the edge coupler's efficiencies?
We are typically something like, depending on what we printed, between 1 and 3 dB. Then of course it depends on the real project and so on, but yeah, so last time, so my colleague had something like 1.5 dB, for example, as yeah, losses, coupling losses. Okay, welcome.
Thank you. Thank you very much. Thank you very much. So we move on with the next speaker from Suruga-seiki. Thank you very much. You can also use this one.
Okay. Okay, thank you very much. Hello, everybody. My name is Takashi, and thank you very much for interest in Suruga-seiki. We contribute to you to provide a simple but very powerful core module for alignment. And oh, really? No. Oh my God. So, okay. Suruga-seiki is established in 1964, and they started mass production of the full automated alignment machine. And we have a lot of discussion with scientists of the university and the R&D engineer of companies. And they had a concern about the alignment. Full automation is too much, but the manual is very poor. So based on this discussion, we took out the core module from the automated machine. So right-hand side, top side is consists of the full, core module, and it is consists of the two fixed motorized stage and the controller. And the controller, there is a Windows PC inside of the controller, and the program also. And it's enabled to the alignment ready to use. And the contact sensor, so right-hand side, top side, we provide a contact sensor. It's enabled to avoid damage of the chip, and also enabled to control a gap between chip and the fiber. And we also, basically this system is designed for the edge coupling, but we decided to add a grating coupler, and it's enabled to connect a vertical alignment. And options like accessory, upper camera, breadboard, holder base and the layer is provided. Most important portion is missing. So we have, yeah, that means animation. Can I? Just one slide.
Yeah, no, maybe we can move to the next speaker and then we can retake that.
Okay, okay.
Yeah, sorry for that. Yeah. So we will move to the next speaker now, and then we can retake the presentation. Is that okay?
Okay, I'll explain my background.
Okay,
yeah.
okay.
So very sorry. So the most important feature is built-in software. So we installed 6 type of the algorithm, and one is field search. It's finding a Gaussian edge. And after that, it moved to the peak search XY, and you can do alignment automatically. And of course, we provided the profiler to record. And the next one, third one is focus search. It includes XYZ for the lens fiber. And we also provided fiber array alignment for the multiple connection. And of course, we provided loop back alignment for the one side. And basically, we are providing 2 6-axis stages. But you can select down. You can do a down selection for the one side 6 automated stage and 1 or 2 side 3 automated axis stages also. So now Suruga-Seiki is not familiar in the Europe, but we are working with Hitachi High-Tech and VLC Photonics. And especially we have a very good relationship with VLC Photonics, and we have a demo unit there. So if you are interested in it, please contact VLC Photonics. Thank you very much.
Thank you very much. I'm sorry about the animations. We can move on to the next speaker from EMEA.
Okay, so good afternoon, everybody. First, I'd like to thank you for the opportunity to be here. So basically, let me just start here. EMEA is a representative company that we are 10 years in the market already. We come from electronics. And 8 years ago, we started with microelectronics department, and 4 years ago with photonics and also battery solutions. You can see that we have such a huge portfolio, but our idea is to bring all the solutions to the table and discuss together with our customers what will be the most suitable solution for his processes. Basically, you can expect from us wafer processing, wafer level packaging, balling, reballing, additive nanofabrication, that I have my colleague here that will speak a few words about that. Photonic wire bonding, active alignments, die attach and related processes. CO2 is no cleaning, plasma, wire bonding, wire die testing. So that's a lot of different technology that we can bring. We have a booth down, so if you need any support in these processes or want to discuss the equipment, a process, or even your product, please come down and speak with us, and we'll be so glad to bring you the solutions to the table and analyze it to you, together with you. Odin, if you want to join me, I want you to speak a little bit about Vanguard.
Yeah. Thanks, Rafa. My name is Mohammed. I work for Vanguard Automation in Germany. I try to make it short within 2 minutes in form of 5 questions. Who we are. So Vanguard Automation is founded in 2017, and we are based in Karlsruhe, Germany. Which challenges that we are trying to actually solve? We are trying to solve the challenge of hybrid integration, namely connecting or coupling light from one chip to another. Basically, focused especially towards the to provide 3.5 gain or laser chips for silicon or silicon nitride platforms. Which technique we are using? Additive manufacturing for sure. It's also 2-photon lithography.
However, specifically, we are talking about two structures, two kind of structures. One is photonic wire bonding. Essentially, it's a polymer waveguide fabricated to connect light from one chip to another, or facet-attached microlenses. In the third option, you could actually also print arbitrary 3D shapes, as you will. What are the advantages? You can actually combine not only passive components, but also active components. So this ranges from lithium niobate or thin film lithium niobate. I think Hyperlight was mentioned. That is one example. Silicon photonic, silicon nitride, 3-5 chips like indium phosphide, gallium arsenide, and the others, as well as fibers. You don't only have the relaxed placement tolerance, but also fully passive, so no active alignment is needed. And then from die level or device level, we could also cover up to wafer level, up to 12-inch wafer. And then we also have actually coverage between surface edge or surface coupling to edge coupling as well. And not only prototyping, but we also cover manufacturing as well. And not only for low volume or prototyping, but also high volume prototyping. One of my colleagues actually mentioned that case already in a meeting last week in TOP conference, that we actually are working closely with POET to actually nail down their wafer level processing. And then not only reproducible, so by reproducible I mean we go down to 0.8 dB per interface loss. And what comes next, if you are interested in more use cases of our customers, as well as, so this I actually suggest to ask you about reliability of these polymer waveguides, please come to our booth. I would be happy to actually mention you all this information. Thank you.
Okay, so just to continue, of course, as a distributor company, we work as a facilitator. Let's say we see that nowadays everyone is very busy and it's very difficult to have answers from the manufacturers, let's say. So here's where EMEA enters and can bring like people that are experts to help you developing your process. We also have local support, so we do installations, calibrations, let's say training, testing, upgrades, maintenance. And basically, this is what I had to tell you today, together with our partners, let's say. We call them partners and not suppliers, because we believe that this strength in the relationship that we have with them is the added value that you can bring to you. Also, a little bit about the reference that we have. So that's different types of customers, let's say, from defense, from automotive, research and development, universities. So it's, let's say, it's very interesting to see what you guys are doing and being supporting you. Thank you.
Thank you very much. There are any questions? If there are any questions, you can visit the booth from EMEA. And then our next talk, it comes from SECFO, sorry.
Okay. Well, thank you very much to the organizers for the opportunity of being here and introduce you to SECFO. SECFO is a cluster that was born 15 years ago as a photonic cluster. We bring together experts from laser, optical systems, advanced sensors, and also integrated photonics. We were leading these photonics to become the strategical technology in Spain, giving visibility to this technology. But then in 2020, we realized that technology doesn't evolve in isolation, so we expanded our frontiers to deep tech. Then we incorporated, as you can see, also microelectronics and semiconductors, artificial intelligence, quantum technologies, advanced materials, and a lot of more, robotics, drone, but also keeping photonics as the central of these innovations. Let me explain a bit of how is our ecosystem now, 15 years now. And then we are more than 160 companies that are mainly technological small and medium enterprises. Also, we have an important percentage, 20% of startups and spin-off. About 23% are also research centers. Then we have also 10% of large corporations that are here in the cluster as end users because they want to stay up to date of the state of art of technology, and they participate also in projects, in events. And also we have incorporated 2% of investors specialized in deep tech that provide these fundings to innovation also and are here to look for startups to invest. But what truly defines us is the impact we have in technology and in Spain. We have about 1,200 experts in deep tech. They generate about 165 patents per year. These are 7 million invested in prototype development. During these years, we have participated in 325 innovation projects and about 180 technological challenges that we have managed for the industry. So I think these numbers reflect how important is collaboration in our ecosystem. We always try to connect the experts with the industry, with the talent also, to keep them connected. And how we do that? We bring together research centers with their investors, companies, startups, spin-offs, the end users, the investors, to foster this innovation and foster also strategic partnerships between them. And that produces in a lot of new business opportunities. We do that principally with high impact networking events, online, face-to-face events. We are a very dynamic ecosystem. I don't know if maybe 1 year we have done about 80 events in a year. That's too much. But as we are a very transversal ecosystem, we are located in Barcelona, but our members are from all over Spain. We need to be this dynamic to keep them together, and we grow together with them. So we just not connect these companies. We also drive innovation. We lead projects. As a cluster, we have a special fundings from the Ministry of Industry that allow us to participate in projects with our members. Normally they participate 2, 3, 4 of our members in a project. So every year we have been developing these innovation projects. Some examples of projects we have led across different sectors are DroneStore, an autonomous 5G drone with artificial intelligence and advanced vision for warehouse logistics. Also in submarine exploration, we participated in Beacon that incorporates laser and LiDAR technology in a remotely operated vehicle for underwater monitoring. In healthcare, for example, QLIV in vitro, in which with optical sensors are used to improve bioprosthetic heart valve manufacturing. Silicon Eye, a real-time monitoring system for steel production using optical filters. TriFirst Compact, an optical demonstrator for progressive lenses in vision health. So there are examples of the projects that we have led in all over these years. So then if you are looking to participate in a strong innovation ecosystem, participating in collaborative projects, SECFO is a place to be, where to find these partnerships. And so let's connect. Feel free to contact with my colleague Sandra or with me to see if we can work together to push photonics and deep tech even further. So you have here our emails, or also we have our booth, so you can visit us and let's discuss of new opportunities. Thank you.
Thank you very much. Thank you very much, Ellie. Any questions for SACFO? Just in case. If not, okay, we will discuss over the exhibition. Thank you very much. So we can move on. Next speakers from DataTech.
Okay, so good morning still, I think. So probably a lot of you already know us, but because it's the first time we come here, let me present myself to you. So we're DataTech, we're a Spanish company. We are experts in test and measurement solutions. So we have a huge catalog in order to fulfill that. So we work with almost all the universities here. A lot of you already know us quite well, but some of you don't. So let us present what we can do for you for the test and measurement side. So to give you a little bit of history on our company, we started more than 20 years ago here in Spain as ICECOM. So you probably know us for that name. But a couple of years ago, some German capital come into our company, and right now we are in 6 countries already, and we centralize our purchasing so we can offer very competitive pricing, and also a huge stock, more than 50 million in stock, which can decrease our delivery time to you. So we hope that that can help you. Going into what within our portfolio, what can help you within our test and measurement problems. I tried to divide a little bit of the families we have here. Downstairs we have a setup where we're more than glad to explain to you with further detail how it works. But I divided here in 4 families. The next slide is the last one. So firstly we have real-time oscilloscopes, AWGs. I think from VLC Photonics already did their setup is pretty. It's basically what you need for the test and measurement setup. So basically a real-time oscilloscope and a arbitrary waveform generator to test all kinds of EMC probes, so quantum sensing, quantum key distribution, and we go up to 64 baud. And of course, you can also characterize your modulation using the active technologies arbitrary waveform generator. And because we try to integrate all the measurement solution within that, we also have the VNAs, the vector network analyzers, where we can go up to, with our enriched solution, for example, up to 220 gigahertz. We've already had here some presentations with some concerns regarding the difficulty on the electrical side to go up those frequencies, and we're starting to have those real-time solutions to measure it. Then on the optic side, we have the optical signal analyzers, where we can do the usual measurements, so light source measurements, spectrum analyzers. And with VNAs, we have all kinds of types, really depending on what you want on this side. So without screen, with screen, and so on. And finally, in order to complete the solution, you need to know how to measure and also to automate processes. So we work with MPI for probe stations. We have more than 15 years experience. Actually, my colleague, who's right there, is our expert in probe stations, and for semi-automatic, automatic probe stations on optoelectronic characterizations for all kinds of optic, electronic, optic, and also for the probes, so RF and DC probes, and also for the calibration services. We also offer some seminars with institutions, like, for example, next week, in 2 weeks' time, we're going to have a seminar in Instituto de Electrónica, de Microelectrónica de Sevilla, And we're more than glad to talk with each one of you to try to understand what you need for machining, and we're more than happy to give you seminars and to go to your facilities and explain that to you. Having said this, we're downstairs, so please, if you have any questions, feel free to speak with us.
Thank you very much, Joel. So the next speaker comes from Ficontech. I just realized that your logo is not in. I'm so sorry for that. But yes,
no worries. No worries. So, yeah, hi together. It's great being here at the Photonics Integration Week in Valencia, and especially thanks to the organizers for adding this session. I think that's quite useful for all the exhibitors and also for the participants here to get an overview, what we are actually doing, and makes browsing the exhibition a bit easier later on. Okay, so what are we doing at Ficontech? Our core business is basically the cutting-edge development of tailored manufacturing tools for your photonic devices. So it can be in R&D or in the prototype phase, but more and more we're targeting high-volume applications with big production lines where we have developed recently new architecture and new systems. You see some process examples here below, so it can be some very precise die bonding, some free beam optics alignment, but in general we are working across, I would say, almost all industries. So it ranges from aerospace to telecom, to defense, to medical applications. And I will not target all these points here. Let's have a closer look on the systems or platforms that we provide. A lot of customers start with these lab scale systems, so they're quite nice. They are open, easily accessible, and great for, let's say, prototype development, R&D, and small volume production. When it comes to, let's say, production environments like this, you basically often need a housing around the machine just for safety aspects, and also for the shop floor integration, cleanliness, and things like that. We're offering systems without, let's say, automatic feeding of materials. So this platform here has an input and output feeder that pushes trays of materials through your machine for high volume and autonomous assembly. This machine here basically requires to be loaded by the operator, and in the very long run, if you have a high volume market to address, we are also offering these production lines. And the first one that we did was for a gas sensor in automotive applications. But now we recently developed, let's say, the biggest one, I think about 25 meters long, a lot of machines interconnected, doing fully automated volume assembly of camera modules within, I think, about 10-second cycle time. So, what are we doing within our machines? And I think that's the most important topic and the thing you really care about. So we're doing passive and active assembly. So passive assembly typically runs based on some train positions or some vision feedback. So you basically use a camera from the top and bottom side to reference to your assembly position. You move your component there and you put it, and then you can bond it eutectically or with epoxy. Another thing that can be quite critical, and this is why we developed this IR through silicon technology on our end, is basically when you have integration cases for silicon photonics where you have a silicon nitride chip and you need to bring indium phosphide laser very precisely with regards to that silicon nitride waveguide. You really need to look through the wafer, see the die from the top side that you want to place, and what we can then do is basically map fiducials on the mount two fiducials on the die that we want to place, and we can reach about, let's say, 500 nanometers at 3 sigma placement accuracy with this technology without activating the device. So, and when we're talking about active alignments, for us the understanding is you always turn on the device and read out some feedback signal. And yeah, for me always a great example case is the one here on the top hand right hand side. What you see here is basically a passive silicon nitride chip in the middle. You have a FAU on the left side that's being aligned initially through some loopbacks here in the circuit, and now, yeah, you want to attach a laser to it. And what we have developed is basically a gripper that can pick up the laser chip, connect it through some probe fingers, turn on the laser, and then you're making basically an active alignment of this chip on the edge through the fiber, and on the fiber side you basically have attached a photodetector to recognize the position. And once everything is done, we have found a good position, we dispense some epoxy on the edge and bond it together. So this is really, for me, an amazing step in our history, and we have developed new grip tools that can also adapt to different electrical patterns on the die itself, so that provides a lot of flexibility. Apart from that, also some camera and free beam optics assembly is what we are doing, and we're offering testing solutions as well. We also have a booth downstairs, so yeah, we invite all of you to just pass by and have some discussion with us. I have a lot of videos with me to show you all the individual processes, so if you're interested how that looks in a real setting, just pass by. Me and my colleague Andon will love to discuss with you. So, thanks.
Thank you very much, Malte. Thank you very much. If you have any questions, you hear Malte already. You can pass by and visit their booth. They will be happy to talk to you. And then we move to the last talk. Yes, it's Spanish Foundries ecosystem.
Well, thank you very much. Good afternoon. Glad to see you again in the Photonic Integration Week. I would like to thank also the organization committee for this nice organization. And I'm here to talk about the Spanish Foundries ecosystem for the photonic integrated circuits here in Spain. So as you can see, is formed by 4 principal fabs. We talk about the IMBCNM, which is in Barcelona, which I am from, is for the silicon technologies fabrication. The 2D graphene technologies is for Graphenea in San Sebastian. Then the 3.5 semiconductor technology is in Spark in Vigo, and the hybridization of all these technologies is here at the UPV fab. So let's talk about the capabilities of each of the fabs. So here we talk about the IMBCNM and Graphenea. First, the IMBCNM is a micro and nanofabrication clean room, so for photonics silicon nitride platform and peak prototyping with these 2 options, which is the multi-project wafer or the dedicated process. It's an ISO quality control certified. We have 2 areas, 1,500 square meters clean room in 2 areas. We have the 10 sorry, 10 class and 40 meter squares, 100 class and 40 square meters of 10 class. The lithography is ensured by a stepper with a maximum resolution of 600 nanometers. Complete CMOS compatible line. We have the oxidation, doping, deposition and etching, 4 and 6 inch wafers automation, and all the needed metrology techniques such as SEM, FIB, FA-tire, ellipsometry, etc. Whereas for Graphenea is a dedicated graphene foundry, a strict quality control ISO certified as well, vertically integrated from growth to device fabrication, wafer scale manufacturing processes, ready-to-use graphene field effect transistors, or what we call GFETs, plug-and-play device, either for early test and proof of concept devices, different designs tailored for your application. It's an excellent platform for rapid device prototyping and development, and 4 or 2 probes devices, and handy format 1 centimeter square dies. The next, we have the Spark and UPV fab. So I think the Fran and Pascual talked previously, like more extensively about. And like for Spark, it's a commercial foundry for 35 semiconductor, which is 16 square meters clean room for wafer production and a research center parallelly. State-of-the-art clean room facility for the medium to large volume manufacturing of 35 semiconductor chips, such as indium phosphide, gallium arsenide, aluminum nitride, etc. And research and development center offering all the additional services towards fully certified photonic products, and the capability and capacity to address a large customer base across a wide range of different markets. And last but not least, the UPV fab, which is an access for short mid-term technology validation and on a clean room environment, which is focused for spin-off startups and also SMEs. It's 500 square meters class 10,000, 6-inch wafer automation dedicated, and deposition techniques such as LPCVD, PECVD, and sputtering, lithography by mask contact aligner, and all the methodology techniques needed for the characterization, such as SEM, FHI, focus ion beam, etc., and for the assembly, microtransfer, and printing, and flip chip. So to summarize, it's 4 pillars. For first, the fabrication of the passive circuits is done by the IMB CNM. Then the modulators of 2D graphene is done by the Graphenea. The active components, such as photodetectors or lasers, are done by Spark. And UPV fab is to hybridize and the assembly of all these technologies into a single chip. And okay, thank you very much. I hope you enjoyed the presentation.
Thank you very much, Jad. We have a booth downstairs if you want to visit and talk to Jad, to Fran Diaz. I don't know how long Fran will be around, but we have here all the people from CNN and not from Graphenia, but they will be glad to contact. They will be happy if you contact them also. So now it's time for closing. But before closing, our colleague Sandra from SECFO will explain us how the business-to-business meeting
we'll go on, okay? Hello, everyone. As my colleague Ellie said and Gloria introduced in the morning, we are the one boosting these B2B meetings. You must have received a list of participants and an email from me. If you didn't get it because you registered last minute or something, you can reach back to me or my colleague to see if we can fit you somewhere in there. And if you want to have a specific meeting, we will see what we can do. But yes, thank you, Gloria. The meetings will be held here in the auditorium. They will be held from 5 p.m. to 7 p.m. at the same time that the clean room and lab visits will be held, so you must choose what you want to do. Each of the options will be fantastic, I'm sure. And yes, you can see there will be up to 15 different point meetings here in the auditorium. You must look for the number that is assigned to you. In the first row, you will see the participants, so you can look there for your company if you requested a meeting or if someone requested a meeting with you. And you will see the timetable down below when you will see in which slot you have the meeting that you requested or someone requested with you. Also, we have another one. Yes. We send the updated planning at the previous coffee break. If you didn't get it, please tell me or my colleague so we can send it to you so you can prepare. Also, if you are not available, you can also tell us, look for us, and we will change it. And also the last planning will be shown here at 5 p.m. so you can take a look at the final product because we've been changing slots and adjusting everything. So yeah, we will be very glad if you want to participate in these B2B meetings, and we are glad to boost this collaboration and innovation. Thank you to the organizers for giving us this opportunity once again to organize them. And yeah, we are at your disposal. If you need anything, just let us know. I think now we will be going to the lunch break, I think. Gloria, yes? Thank you, everyone.
Thank you. Just one last comment about what Sandra just mentioned is that, for example, at the beginning we had planned like 9 meeting points here around this room, but then because there is so many people who want to meet each other, if you have a booth, for example, number 14, I guess, no, I just saw it. Yeah, number 15, for example. No, Seconex, no. Okay, no, it was on the previous one. Yes, sorry. For example, FineTech, we can have from FineTech, it's column number 7. We can have these meetings, for example, directly in your booth. So we have your booth. I think it's a very good option to have the business to meetings over there. But we will give you all the instructions after the lunch break, okay? So. Yeah, this will happen at the same time. If you have a meeting, you can talk to the person who wants to meet you, and then try to find another time. Maybe if you want to also to join the lab tour. The lab tour will take just not the whole 2 hours. It's just maybe half an hour, 20 minutes, something. So you will have also time to meet with anyone you wish. Okay?
So the lab tour starts at 5 also?
Yes. Yes, after the. Sorry?
We need to decide between the lab tour and the business-to-business first.
If there is also a lot of people interested on the lab tour, we can have an extra lab tour session, an extra lab tour group after the business session, and then there will not be a problem for that. That would be great. Okay, any other question, comment, or so please check the file. Find your name just in case someone wants to meet you, and that's it. Thank you to all the expositors and the sponsors. Please, I would like to thank all of them again. And I think now we are ready to have lunch and have a break. Thank you very much. está. Uf, venga. Do you want? No, it's. Do you want that one on the screen?
Third one, third one. Next. This one, yes.
This one? Okay, I will ask to the guys to put it down.
Thank you.
Is that okay?
Thank you. Hi, すみません。
Okay, so welcome back to this afternoon session. We're having session 3. We're going to talk about a very important topic in our environment, in this ecosystem. It is about investment and growth on photonics. We are having this talk by Ismael Rodrigo from CDT Invierte. If we can welcome our speaker, thank you.
Good afternoon, and thank you very much to the organization for giving us the opportunity to introduce to you all the tools that we have to support venture capital investments. My name is Ismael Rodrigo. I work for the department that is in charge of managing venture capital programs in CDTI, and in particular Invierte. I've been involved in Invierte since its creation. I'm going to give you a little background. CDTI is the Spanish innovation agency, and mainly its core business activity is to fund R&D projects, but it has also other goals as support the creation and consolidation of technology-based companies, and it does also with some grants as Neotech. But it was also decided that to have some experience in venture capital, and it created Neotech Capital Riesgo. It was promoted by CDTI and the European Investment Fund, and with this program, invested directly in 315 companies, more than 780 million euros. Anyway, all these funds and co-investment agreements were not as technological as CDTI wanted at that moment, so they decided to create Invierte with the Invierte program, and a closed-end collective investment company that is supervised by the regulatory body of national stock market, and it was created this company was created in 2012, and at the beginning it worked more like a fund of funds. We launched calls in different areas. I mean, in ICT, in bio, or in industrial technology and tech transfer, and we supported 14 funds and 3 co-investment agreements, and we invested in 231 companies, more than 870 million euros. This has been the seed of the initiatives, or the capital initiatives that we have right now in Invierte. We have direct funding initiatives and indirect funding. Direct funding, in this previous experience that we have with the co-investment agreements, we have to invest also in companies directly with a co-investor. So in 2019, we created the co-investment program with accredited investors that I'm going to explain in detail later. An evolution of this co-investment with accredited investor has been, or an evolution or some particularities, has been the investment in strategic companies. And we keep also the indirect funding, all the funds that I have presented before, in which ones Invierte has invested with previously to these funds, 274 million euros. Are right now in divestment period or totally divested. But in this indirect funding that I'm going to present, we have some funds that are in the investment period, a call that we launched in tech transferring, and the fund of funds that we have launched last year. There are 2 key features that we have to take into account is that Invierte's activity, in opposite to the CDTI that is normally under the state aid framework, Invierte's activity is in pari passu conditions, normally with private investors. Okay, and also that normally the companies submit all the proposals to the CDTI for grants, but with Invierte, the contact is mainly the investor. They need an investor, and it's no longer the company, it's the investor. That doesn't mean that we don't speak with the companies, and many of the companies that we have funded, they have contacted us, but they need a private investor. Why direct funding? Well, there are many reasons. At the beginning, we thought that the national dimension of the funds, that sometimes they are not big enough to grow the company to a certain level to be profitable. Sometimes they have they cannot fund the company enough, and there is an asymmetry in this profitability because the other investors or the other buyers of the company, they get most of the profitability, and therefore there is less investment in venture capital. Also is to share the risk of the operation. We, as CDTI, we are I don't know how to say, but I mean we are eager to have to fund disruptive technologies, and we are of course accept the risk profile of these companies. And the private investors is a cherry picking operation. That means that the private investors can submit us the operation that they want. I mean, because due to the risk of the operation or due to financial difficulties to fund the operation. How it works? We have to accredit. We have to the accredit, or we have we have an accreditation of private investors, validation of the investment proposals, and tracking of the investor and the investees. Which are the accredited investors? Well, what we ask is that they have to be private professional investors. Okay, they can be regulated as venture capital operators or closed-end collective companies, or they can be big companies that they fulfill their requirements to be professional investors that are there. They have to have previous experience, that is not too much, but I mean some experience, and active management. That means that we can co-invest, but they have to have a board member, is something that is compulsory for us. They have to have also a team in Spain, and of course, well, funds from tax haven are banned. Which are the companies that we are going to co-invest with them? We are going to sign the co-investment agreement with these private co-investors. It's the same one, is in our web page. And the companies that we can fund or we can co-invest are companies in which ones the technology is the source of competitive advantage. That means that in the business plan, I mean, it has to be clear that it has the technology a key role in the company. They have to be Spanish firms, and we are also to introduce some clauses in the shareholders agreement to be Spanish ones. We can invest between 50% and 90% of the private investment. That means that if the co-investor can invest 1 million, Invierte can invest 500,000 or 900,000. This is up to the private investor. Normally they ask for the 90% of the investment, but in some cases when they don't need the 90%, they ask 50%. But we have a minimum. The amount that Invierte invest per round is between 500,000 and 10 million. but it's true that $250,000 is acceptable if the company has a special interest, technology, or a disruptive technology that is considered as very valuable. And the maximum that Invierte can invest per company is 15 million. And always with a public share less than 40% of the cap table. There is a difference between regulated vehicles and non-regulated co-investors. That means that if we co-invest with a non-regulated, that could be a big company, I don't know, Repsol or whatever, and we cannot have together more than 50% of the company. This is just because we don't want to fund or we don't want to have control with a big company, because that could be an aid, and this is not the case. We invest as in pari passu conditions, and this is something that doesn't happen with regulated co-investors. That the goal of these investors is to make money, and it's clear that having control can be an option or not. But with a big company, it could be something that is not acceptable for us. And the co-investor must have a board member, as I said before, and they receive a success fee when the company is divested. The other direct funding is the investment in strategic companies. During the operation of these co-investment agreements, we have checked that some companies could be considered strategic companies by our board, and that means that the round has to be more than 30 million, and the Invierte's investment is going to be higher than 10 million. This is for supporting the growth and consolidation of Spanish technological companies, and the idea is that we always have to have less than 40% of the capital of the company, and we cannot leverage more than 49% of the round. But this has been not very usual, but I mean, we have some strategic companies in this period. With this direct funding, we have 169 accredited investors, so we have signed agreements with 142. This could be also a little bit tricky, because any management company has to sign, if they have different funds, so they have, I don't know, Fund 1, Fund 2, Fund 3, they have to sign a co-investment agreement, because they are different funds, they have their anti-money laundering processes and everything, so we have a higher number, although the management company could be the same one for different vehicles. We have approved 160 companies and more than 500 million euros, and we have closed 149 companies, and in which one we have invested more than we have invested 380 million euros. It has done that at the beginning of this year we have communicated to our co-investors that we are trying to reorganize, and we are going to post the investment for new companies. We gave them a deadline for the 7th of February, and we have right now 30 new companies in analysis for investment that we are going to post right now this co-investment, because till now we have been agile and fast resolving all of this, but right now we have a certain bottleneck between all these companies that we have invested, also other companies that we have from the co-investment agreements, that we have also other 15 companies before, the funds that I'm going to explain later, and the funds that we have previous. So we have to reorganize a little bit, and I believe that before summer we are not going to resume the co-investment line, but hopefully after we can resume this co-investment line. And there you have the links to see some of the investment that we have carried out, and also some list of the accredited investors. Above all the public investment, because some of them they ask for some confidentiality period that they are doing around, and they don't want to be published yet. In photonics, we have different companies: KD, Woodtick, Halcyon, Metlumix, Villa. Only in these 5 companies we have invested more than 17 million euros, but we have other companies that could be in the photonics area, I don't know, to Ice Vision or Dana Medical that are also included. We have also invested in Graphenea, although we have divested, and it's a sector that I'm gonna say that is we are horizontal, but we invest in technology companies, and of course is part of our portfolio. Regarding to indirect funding, why we invest in indirect funding? Well, first of all, because we see that there is a lack of private capital, probably because the profitability this year has not been as good as the private investors want, above all in technology funds, that they don't have the required size that they need to make money, that we can act also as anchor investor, and that we want to promote technology. Right now in 2024, we are going to invest in any stage, in pre-seed, seed, venture capital, private and growth, and with funds that has a minimum of 50 million euros, and they are specialized in technology. Before we launched a call for technology transfer funds in 2021, although I believe most of them they started in 2022, and we committed to invest in 120 million euros, 40 million per fund in 3 funds, in Beable, in Clave, and in Bullnet, that are in areas that can be similar. Some of them, as Beable and Bullnet, they invest also in this sector, and we wanted to promote this to facilitate this technology transfer and try to foster the ecosystem of these innovative companies. All these funds are right now in investment period, and all of them has performed, has invested in more than 7 companies for sure right now. In 2024, we launched another new area that is funds of funds, that is in any stage, at any stage. The funds has to be specialized in technology. They has to have a majority investment in Spanish companies, with a majority of private commitments, more than 50 millions, and Invierte has to have a minimum investment of 10 millions. The idea is to have more funds that they can invest in technology at any stage. The result of this fund of funds is that in 2024, we have approved 25 funds with an investment of 1 billion euros. And right now we have close commitments in 13 funds with more than 800 millions. And we have just launched a web page in Invierte that you can see how this initiative goes, and the portfolio. In the portfolio is everything mixed. You can select the funds or the companies, and these are the tools that CDTI has to support venture capital investment. Well, that's all, and I'm open to your questions.
Okay, so if we have any questions for Ismael, you can raise your hand.
Thank you, Ismael, for the presentation. You mentioned the strategic investments. So is this something that you are actively scouting, or when a company comes to you, you determine whether it is strategic or not?
Well, it's a very good question, to tell you the truth. It has been, at the beginning, it has been more a necessity. I mean, some of the companies, they need to fund some rounds, some big rounds, and it was a necessity. And it was together with our board that they decided that to create this new line. Right now, it's not something that we are promoting. All of these companies that I have mentioned, we have only 5 strategic investment, but we have a procedure that they have to ask. We submit the proposal, and it has to be solid to our board, and they decide if we continue with the study or not. But to tell you the truth, I mean, it's not something that, I mean, it has become more a necessity at the beginning, and right now it can be on the opposite. Some companies, they can submit. But it's true that many companies, they would like to be strategic, or they would like to be considered strategic, and it's not going to be possible. So it's not easy. I don't know if I answered your question.
Okay, any other more questions? Okay, so I think we are ready to thank Ismael from CDT. Okay, so we are going to prepare our next talk. It is given by Guillermo Gomez from SET.
Okay, thank you, everybody. Thank you, the Polytechnic of Valencia, for organizing this event and invite me to present our Spanish Digital Investment Hub strategy. This is the vision that the government of Spain has in terms of promoting Spain as a hub for digital investment in our country. So the Ministry for Digital Transformation and Civil Service is the ministry in charge of developing the digital strategy, covering different verticals, semiconductors, AI, quantum, and so on. And as a part of this strategy, we have our flagship project, which is the Spanish semiconductor plan called PERTE-CHIP, that will allow us to enhance the value chain and the industrial fabric in the semiconductors. This program is backed by 12 billion. Okay, so if you look at the numbers, it means 0.9% of the GDP of Spain. So if you compare with other countries, that means a lot. We are putting a lot of efforts in developing this industry. The plan covers 4 areas. So we finance activities from scientific capacities through design to manufacturing of semiconductors and the end user industries consuming those chips, such as automotive, telecom, and so on. We have different instruments to finance different project types. We have grants, normally for R&D and educational activities, or let's say flagship projects in the framework of the European Chips Act, namely the foundries we have been seeing over the last months and years. We have equity and loans for venture projects, scale-ups, startups of new developments in the semiconductor sphere, including photonics, of course. And then we have cooperation agreements, and we engage with international institutions or research centers to set up a common project in the field of semiconductors. So we don't start from scratch. As you know, we have different strengths in our value chain, namely RISC-V integrated photonics, quantum computing. We do manufacture quantum computers in Spain, Spanish-made. And then the semiconductor scientific capabilities, what we call the lab to fab approach, it has been explained so far during this morning, and the end user industry. We rely in our industrial sectors. As you know, we are the second largest car manufacturer in Spain. We have the second world largest fiber optic network here in Spain after China, and other industries that are getting bigger, such as the data centers, for instance. Let me explain two of our major assets. One is RISC-V, and the second is integrated photonics. First, RISC-V, we want to be, we are in the way of becoming the new international pole for RISC-V development around the Barcelona Supercomputing Center, which is an international top-notch institution in the field of HPC and also RISC-V design. We are putting 1 billion on the table to mobilize this action. Okay, so the Barcelona Supercomputing Center has already the 8th most powerful supercomputing in the world, and they have an excellent team doing RISC-V design as well. So around the Barcelona Supercomputing Center, there are different spin-offs. For instance, OpenChip, doing HPC accelerators and HPC cores in RISC-V, and also Semidynamics, doing AI cores in RISC-V. Each of them endorsed by these figures you see there in grants for the central government. So, and then we are in conversation to establish design centers in RISC-V through international collaboration with also very active players in RISC-V. So that means that we are looking to develop chips made in Europe, made in RISC-V, that eventually these chips will go in servers for HPC and then broader applications such as automotive or data centers. And these chips will eventually consume other components such as transceivers, couplers, and any other switching elements that goes later on in the data centers. So then let's switch into the integrated photonics sector. Spain has one of the leading end-to-end integrated photonics sectors. So here in the audience you have a representation of how the value chain is integrated, not only in Spain, but also in Europe and internationally. And we are promoting and backing these efforts with the pilot line, the European pilot line. So as explained today by some of the speakers, the Spanish government is backing the development of the European pilot line in photonics, and with the leading role of the Spanish institutions such as ICFO and other hosting entities such as the Polytechnic of Valencia in Spain. And we have also a vibrant ecosystem in quantum key distribution technologies, photonic fabless, photonic fabrication in compound materials and 3.5 and so on. Okay? So let's look now at the per-chip programs. Okay? So this is programs with grants. Okay? Purely grants. So the idea is to develop in the row above. You have the programs to develop the talent and education and scientific capabilities, and then we have the scientific infrastructure in the lab to fab approach. Okay, so what we have launched so far, first we have the chip missions with the collaboration of CDTI to reinforce the R&D development projects in the semiconductor sector, including photonics. Then the chip company university chairs, we have been discussing about that this morning. So basically we are putting on the table 45 million to co-finance up to 80% of the cost by the public sector, full cost, and the other 20%, give or take, is funded by the private entities. So we managed to fund 15 of these chairs at the universities, and each of these chairs is focused on
photonic design or semiconductor design or manufacturing. So the idea is to create a critical mass of talent at the universities to cope with the increase of the demand. We are seeking to enhance here in Spain. So we did the same for AI, so the AI university chairs as well. And then there is another grant programs to close the initial actions we did with this partnership program, such as the IPCI on microelectronics. So the Spanish chapter of the IPCI is 500 million out of the 8 billion in the EU. I suppose you are aware of the importance of the IPCI. Basically, we are financing photonics, tool manufacturing, or backend as well. And then we have another programs for proof of concepts to develop new prototypes at the research centers or the universities. So if we look at the other line, we are already allocated 67 million euros to our national research infrastructure clean room. As mentioned in the previous sessions, we have like the National Research Council, which is the state, the state research agency, and we have the centers in Barcelona. Then we have Seville, and then we have Madrid, and then we have the regional infrastructure covering Barcelona again, then Madrid, and then Valencia, the so-called micro nano fabs. So those 5 centers are the core of the clean room infrastructure in Spain, and together with the university clean rooms, okay? Then we have our supercomputing network. So we have devoted 156 million euros to enhance the capabilities of supercomputing, classical and quantum supercomputing, with the Mare Nostrum 5 at the Barcelona Supercomputing Center as the central node of these capabilities. And then quantum computing, we have another quantum computing program to finance quantum computing at the sensor level, computation level, and other areas such as quantum algorithms and so on, okay? So together we have this lab to fab approach to allow SMEs, research centers to access the public infrastructure and to develop new prototypes to enter in the market. So this is what we call the strategic investments, okay, that are to be seen together with the grant programs. First, back in May 2022, our president announced a collaboration with Intel and the Barcelona Supercomputing Center to develop the new post-exascale chips or supercomputers that will be the standard in the following decade, let's say, okay? Then in November 2022, we announced the arrival of Cisco in the first ever in the EU chip design center for networking. They are established in Barcelona with a team of more than 40 people. And then last but not least, IMEC. So IMEC announced, together with the government of Spain and the regional government of Andalusia, well, the intention, or is a fact already, to establish the first outside Leuven R&D fab in Spain, and it will be located in Malaga. It is a project driven by the central government with the collaboration of IMEC, and with a total budget of more than 615 million euros. Okay, so the works are already have already started with some surveillance of the sites and the basic engineering. That is to give you an idea and flavor of the photonic integrated photonic value chain. I don't know whether it's the updated one, Pascual, but I'm sure it's pretty complete right now. So we have everything from R&D to foundry services, through design, fabless equipment, and end user industry, all well connected and well coordinated, let's say. Then this was the part most covering the grants, the institutional support, and the flagship projects under the partnership. But how do we finance the industry and the new opportunities? So the answer is the set that stands for the Spanish public entity for the technological transformation, which is the Spanish investment arm within the Ministry of Digital Transformation to drive this technological transformation. So what do we do? Basically, we have a big pocket of 60 million euros, okay, distributed along 3 axes, 3 verticals. First, per the chip, with 2 subcomponents, direct co-investment in companies, or blended financial instrument to finance, whatever makes sense to help to increase the large manufacturing capacity in Spain, basically foundries or backend. Then we have the Next Tech Fund covering deep tech in general, quantum, AI, software, and we have direct co-investment in companies or indirect co-investment through funds, okay, like a fund of funds. And then we have the Spain Audiovisual Hub. We finance direct or indirect co-investment in both audiovisual technologies, such as virtual reality and others, and also production of content, content production. So let's focus on the partnership, okay? All the funds works in a similar way. Basically, we are like any other venture capital, okay? But we have no minimum, well, we have a minimum ticket of 500,000, and we have a maximum ticket of 10 billion, okay? Well, less because we have already invested some. So basically, we have no maximum ticket, and we can cover startups, scale-ups, or future Series A, B, C. We are flexible in framing these operations, okay? We can invest together with private investors, with another public investors. We can create companies, we can create joint ventures, newcos, and so on. The only limitation is that the company has to be established in Spain, okay? And it needs to create some Spanish value, okay? The idea is if we are financing some activities, the core of the activities should happen in Spain. Even if you subcontract, you can subcontract some of the activities outside Spain, of course. We can co-invest with the totality of private investors up to the 49%. So we can meet the so-called pari passu conditions, okay? So we operate under market conditions. Up to the 49% of the round, and we cannot have more than 49%, well, 50% of the total shares of the company, otherwise you will be public, and nobody wants that, okay? We operate under commercial law, so even if we are public, we don't operate under public law, we operate under commercial law. That means we are quick, okay? We can close operation from 2 months to 3 months or 4 months, even faster than that, okay? We closed already operation in 1.5 months, so we can be faster than other VCs. And there is a significant reduction of financial and tech risk because of our due diligence we undertake in-house. So we have a team of technical experts, financial experts, and legal experts covering various domains such as photonics, AI, chip design, and others, okay? And basically our role in the board and in the governance of the company will be this of minority and non-interfering, okay? We will have just the same rights as the private party would demand, okay? That is the idea. Of course, we can talk about flexible investment times, investment cycles, okay? Of course, we invest in profitable undertakings, of course. But we can look at the undertakings from a different angle than a traditional venture capital. And this is just some key figures of Spain as a destination for investment, okay? Our GDP is going very well, so, okay? Our growth is 3% right now in 2024, well above the EU average. And you know, the economists told us last year that we were the world's top performing economy in 2024. The employment, if you look at the statistics, we create 1 every 3 jobs in the EU, okay, right now. And we are, well, the 4th economy in the EU by a number of scientists and engineers and STEM careers production, okay? Then we have one of the best connectivities in fiber optics and 5G in Europe, the 2nd largest fiber optic in the world after China. The 2nd worldwide high-speed train network in the world after China. So you can go from Madrid to Barcelona in 2 hours, from Madrid to Valencia in 1 hour and a half. That means mobility of talent is very frequent. You can live in one city and work in the others, like 3 days a week. And last but not least, we have the cheapest energy right now in Europe, okay? Because the Spanish government have been investing so much in renewable energy, solar and wind, that we have unbeatable prices right now, given the cheap gas supply from Russia is no longer an option for Central and Eastern Europe. So with SET, we already financed more than 900 million euros. Well, this is not updated. Probably it is around 2 billion already. And we financed a lot of, different companies covering semiconductors, photonics, also AI, quantum, and so on. For instance, Design Center for Alternative Architectures, like RISC-V. Equipment fabrication, this is the company Bootpix, doing measurement for wafers and blank wafers. AI-powered sensing application, this was already announced, is Sensia, doing nanovolumeters. Cybersecurity trust, chip design and testing. Chip design for critical aerospace application, and we have a very big deal flow as well, covering an integrated photonic 3.5 foundry that will soon be will see the light very soon. New materials fab, new materials substrate manufacturing facility, quantum and AI application. For instance, our minister announced that today in the Mobile World Congress, we are investing 67 million euros in multiverse computing, which is a company based in Spain for quantum algorithms, compressing the large language model down to a 10% of the total size, of a total round of 150 million euros. So just to give you a sense of what we are doing with SET, we are flexible. We can invest in different size of investments, and we can be very quick, okay? So thank you very much.
Thank you, Guillermo, for this talk. Do you have any questions? Okay, it looks like Pascual has another question. That's great.
Thank you, Guillermo. And probably that was also a question for Ismael before. So you describe how you invest and where you invest. But what are you looking for in return?
We are looking for a return in terms of money and also job creation, return to the Spanish economy, okay? But also we need to see the economic value and the economic profitability of the company, because we are putting equity and we are putting loans, so we are putting the money of the government, so we need to see some return. This is not for financing R&D. We can cover some R&D activities, high TRLs, namely, that are included in the business plan. but this business plan should make sense from the economic perspective. No?
Okay, thank you so much for this talk, Guillermo.
Thank you.
Okay, so our next speaker is Alberto Diaz from Be Able Capital. Let's welcome Alberto.
Perdonad por este pequeño momento, ¿vale? Hay un vídeo en Vimeo que se llama What is Science Equity, que se puede ver en los móviles, pero por lo que sea que estamos teniendo un problema, que explica la actividad inversora de Viable Capital, ¿vale? Nosotros lo que hacemos, what we are doing basically in Viable Capital, that we can see it on the video I was talking about, this is What is Science Equity, which is on Vimeo platform. Explains our investment strategy. Our investment strategy focus on investing on early stages of low TRLs technologies, which are just deep technologies. We do not invest on digital projects, and we do not need to have an entrepreneur, or we do not need to have a startup. Okay, we create startups. We are venture builders. We focus mainly on investment fields with a very high potential for growing. And basically, as I have mentioned, we are just on early stages. We can invest from 200,000 euros to 4 million euros, and we go with the startups up to the Series A. Okay, after Series A, we have the intention to get out and to make cash out for our investments. We are long-term investors. We are not scared of investing on low TRLs. We know what risk is. 50% of our investments on the first year die, and the remaining ones die after also 50% after the second year. So we know that this is a risk game. That's why at the beginning, we invest low amounts. Although we have these investment schemes with these amounts we are talking about, in our experience, we multiply our investment by 1.7 times with grants of loans, other co-investments from private or public investors, such as CDTI, and we are focused on building the company from the very beginning, and we are very hands-on. We are very close to the companies until they have a team that can go on with the project. Our investments, at the very beginning, we are talking that we have companies with just one team member, normally the CTO that we hire, and when the first stage, which is called proof of concept, because we invest in proof of concepts, we try to join to the team and to the project CEO. Okay, the CEO needs to have managerial capabilities, and he's the person who is intended to take the company to a break-even moment and then to make the EBITDA grow. Okay, so we are specialists in doing this type of investments. There are not many in Europe doing this. In Spain also there are not many doing this. It's a very complicated investment area, which is the so-called Valley of the Death. So we are experts in that moment when, after R&D, the research centers cannot move forward because there are no funding for going beyond. Normally there are no further funding to go beyond this TRL 3 or 4, because normally market is there or other investors are there in TRL 8 or 9. So what happens between TRL 3 and 4 and TRLs 8 or 9? So that's our investment area. Okay, our goal is to, and our mission is to capture the value that we see there is a lot in those low TRL scenarios before the private investor or standard corporations are willing to further invest. Okay, so in the end, that's our investment strategy. So maybe we have the video. I think maybe we can be lucky because it is going to explain very quickly all what I'm referring to about. And well, but the fact is that we put a lot of effort in defining a very strong IP strategy from the very beginning. We put a lot of effort in defining the strategy that the company has to follow from the very beginning on terms of protection of the know-how and the knowledge they produce. It's not. We have a very big expertise in our team regarding patentability issues and secret trade and IP issues, because it's very important for this company to create value from the standpoint of IP. And we are experts on all this type of investment matters, because at these stages it's very important to be aware and to be strong on IP issues that create later on a lot of value. We have noticed, okay, so let's make a break. Thank you very much. This is the video I wanted to show to you. So if you can please go there.
What is science equity? Let's start from the beginning. Science equity is a new asset class. An asset class is a group of financial instruments which have similar financial characteristics and behave similarly in the marketplace. One of the main characteristics they have in common is the relevant investment sector. To find out, let's talk about deep tech. Deep tech is a group of technologies that, according to the European Union, is essential to enable Europe to achieve a sustainable and green revolution, a significant improvement in the life standards of its citizens, influence on third countries to promote European Union democratic and solidarity values in the world, and independence on strategic matters as energy, semiconductors, or raw materials, to name a few. It is time for Europe to build a strong economy, and deep tech is the answer. Deep tech involves disruptive technologies and has two main pillars: digital technologies and deep science, industrial technologies. When we talk about digital technologies, we're talking about artificial intelligence, blockchain, big data, machine learning, cybersecurity, etc. When we talk about deep science, we're talking about nanotechnology, new materials, photonics, biotech, micro and nanoelectronics, quantum computing. There's a third group of techs with characteristics of both digital techs and deep science, and depending on if the most important features of each project are linked to digital techs or deep science, it will belong only to one of these two groups. In this third group, we are talking about algorithmics, Internet of Things, advanced computing, advanced manufacturing, agrotech, robotics, food tech, and digital health. So, what are the main characteristics of digital tech versus deep science? First, the type of technology. Digital tech usually uses known technologies and applies them in new ways. Deep science is focused on new technologies. Second, intellectual property rights. Digital techs have a low IP profile, while deep science has a high IP profile, mainly involving patents. Third, the source of the technologies. With digital tech, there are mainly innovators, while on deep science, we're talking about research and development on scientific environments. And lastly, development time. Digital technologies have a medium-term time to market, while deep science needs a longer timescale. Now it is clear that the investment focus of science equity is deep science. Let's see what peculiarities it has. Deep science, coming from research and development, and due to its complexity to be transformed into a commercial product, it means that pre-seed, seed, and early stages phases are essential. And this is because deep science needs a highly specialized investment vehicle in these early phases in order to identify, invest, and accompany these new technologies, and this is science equity. So the place of science equity within the private capital ecosystem is mainly focused on these early phases, pre-seed, seed, and early stages, until other actors such as venture capital and private equity enter into play. So now we've seen the whole picture, we can define science equity accurately. Science equity is a new asset class comprising funds obtaining profitability investing in pre-seed, seed, and early stages in deep science.
Okay, thank you very much for playing the video. So I think this helped much better than my explanation, but in the end what we do is focusing on technologies which are out of the R&D research centers, and we put money and efforts to make them something that within 5 to 6 years become something important in the market, in growing markets. We need to choose, for us to choose an investment opportunity, we need to have the certainty, well, it's not always so clear, but we'd like to have a certainty that the market in which this technology can be developed is growing very fast in the next years, and because the investment stage is so risky, so that we at least need to have this kind of feature for investing. And I think the video speaks almost by itself. I don't know if you have any doubt, but we do what is mentioned in the video. We cover this gap between TRL 2 or 3 that is the end of the research centers and universities, and then we try to push the technologies and the startups until they can reach the market and other investors can join the investment efforts. So that's what we do, basically.
Okay, so let's thank Alberto for this important talk. If you have any questions to Alberto. Okay, so
Okay.
I think we can go to our next talk. Oh, sorry.
You mentioned you fill that gap from tier 2 to 3 up to 4, 5. I don't know how far you go with.
Up to 8 or 9, let's
Okay.
say, until we have the product.
How do you go with the company? How do you accomplish? How do you?
Well, the first 2 years, let's say we're almost venture builders. We design almost everything, because unless the project comes with an entrepreneur that has previous experience, I mean, as we invest so early, and there's still a so long run, because before we get into the market, we like to avoid I mean, let's say the training period for everybody, so that until they become a cool CEO, so we don't have that time, because we are so back in the moment, because we cannot spend 2 or 3 years waiting so that some guy in the team learns to be a cool CEO, for instance. Okay, so we like to hire experienced people with a lot of experience. You have to pay for them. We pay them good salaries, and we are behind until, to make it very simply, until the company has 8 to 12 people, we are very on the daily basis of the company, okay? Once the company has its own team and they have their own financial controller, seasoned experience CEO, and they have their good commercial team, until that moment, we are, every month, we are with the startup, we are asking them, we try them to avoid the mistakes that we have seen many times, because some of them are very common for most of the startups, independently on which industry you are, on which are the technologies. Many mistakes are quite similar at the very beginning, on the early stages. There is a lot of know-how, and we try to avoid the pain of going through things that we see constantly on companies which are, let's say, they are alone and trying to learn everything. So we tried about those pains. And another thing which I think is very important is that when we see that some project it cannot move forward or will not create enough value for investors, we kill it very quickly. Because one thing that, in my experience, I have noticed personally, that in many parts of the European ecosystem, you have a lot of zombies. These are these startups that are always startups, and then they spend 15 years and they are still startups. So that cannot happen. If we see that, in our opinion, if we notice that a company is not growing fast, it's not a startup, because it has to go up sometime in life. They have to go quick, because we have to be, sometimes we are a bit nasty, but in the end, I think people, it's better for everybody involved. One thing is something very complicated and that nobody else do. Another different thing is something that has a value, because technology is always complicated, but the startups should be also profitable, So what happened in this ecosystem is that we notice that there are many cool projects that are so interesting, but they are very complex. There are very deep minds behind them, but maybe it's not for them to be a startup. Maybe it's for them to be another thing. But if you want to be a startup, you need to get the road as soon as possible, so that you grow very fast, because there are competitors, market is changing very quickly, and we try to avoid the pain of being there trying and with no a clear horizon behind. Okay.
Okay. Yeah. Thank you.
Okay. So thank you so much, Alberto.
Thank you.
Okay, so let's welcome Alejandro Maese from AG Photonics.
Hello, everybody. Thank you very much for the opportunity of being here. I am Alejandro Maese. I'm co-founder and technology manager of AG Photonics. And I'm here to talk about our experience or of the perspective from a startup with the investment mechanisms and how it was basically the first couple of years in this project. So first of all, I would like to talk very briefly about AG Photonics, who we are and what we do. So our mission is to facilitate access to optical wireless communication systems through total system integration on miniaturized chips. And our vision is to transform the way people and devices connect by providing innovative, reliable, and efficient solutions. So about who we are a startup. We are a spin-off from the University of Malaga, particularly from the Photonics and RF Research Lab, and we were founded in May 2023. And coming from that group, we are experts in the design and characterization of integrated photonic devices, mainly coming from the telecommunications perspective. So from the research group, for many years, over 20 years, we were working in different type of devices, mainly metamaterial-based silicon photonic devices, also integrated optical antennas, and of course the interface between optical and microwave systems. So the company comes to based on the problem of the current telecommunication systems, which are basically based on optical fibers or radio frequency links, and the limitations they have in both cases. Okay. Also, because with the increase of the telecommunication systems and the necessities, the demand for data, we see that on the one hand, optical fiber has a very high data rate, but it's also very costly to have deploy, and also requires time. And in some cases, you cannot reach certain areas so easily. And on the other hand, radio frequency links, they're low data rate. They're not very secure because you have basically the signal going everywhere, and the spectrum is very limited because of the high cost. So the solution is to bring optical wireless communications just to not as a individual solution, but just to coexist with the other two solutions that are right now in the market. So the idea is to solve this, to bring a solution in this gap, so that we have high data rates at optical speed, optical links, in wireless environments, also enhance security. For example, applications for ground-to-ground or ground-to-air connectivity, with especially now that they're coming very dynamic environments with non-terrestrial networks, drones, and so on, to have this very dynamic communications with low power consumptions, and also easy of deployment compared to, for example, fiber optics. So our technology is based on the reduction of the size, weight, and power consumptions enabled by silicon photonics, mainly. So compared to current commercial solutions are very bulky and based on like a set of different components that are aligned all together, what we are betting is for a massive integration in a small form factor, reduction of cost, because we're leveraging semiconductor fabrications, and also the ease of deployment. So we're going to very small chips in which we integrate the whole system. So in our technology, we are using optical antenna arrays with electronic pointing, carrier modulation and reception on the same chip, and also new antenna topologies that are drastically reducing the complexity of pointing and tracking. We have already a portfolio with several patents, and working on, of course, increasing or boosting our technology as fast as possible. And of course, potential use cases are not only the backhaul, but also last mile connectivity, especially in areas in which are not easy to reach, for example, with optical fibers, like islands, or very disaster areas in which basically communications are breakdown. Also like industrial areas which are already very dense with, for example, Wi-Fi communications, but also taking a look to high security links in defense applications, or intersatellite and non-terrestrial network links. So now in the previous presentation, there was also talking about deep tech, and I think there's several points that are common to all the different deep tech areas, but it's basically they're based on some scientific breakthrough. So it requires also a very long time, because usually you need also to further develop the proof of concept. The idea is coming from something that nobody has ever done before, and usually many of those startups are coming from spin-offs from university or research centers, and very focused on hardware or IP development. In that case, as in the previous presentation, Sometimes this first core or of the management are basically technical management, so PhDs, professors, and so on, which are not so really deep experience in business in many cases. And it requires also highly qualified technical staff and very specific and expensive equipment, like for the labs, also sometimes very specific softwares for simulations, fabrication in case of hardware, which is very costly. So that involves very long non-recurring engineering phases compared to other startups, which means that the project itself requires of a very long initial phase, and also is very capital and time intensive. Not only that, but it many times is a focus on creating the value. What is differential? What your company is different from other startup, and this is very important, especially at the early stage, because we have also different risks compared to other startups. Like on the first hand, the technology is that you have a concept, but how this concept is going to work. And second is also if there's a demand on the market already, or you need to create the demand, you need to make the people like what you're doing. Once, in many cases, once you are already in the market and you have created, or there is a demand, a clear demand, the advantage is that you have very lower competition because you're the only one there. So that's why, compared to traditional startups, the very early stages, the survival rate is lower because because of those factors. You need longer time, it's really expensive, you need a lot of money, basically. And once you reach a certain level of maturity and you're creating the market, then sometimes the survival rate in posterior or in later stages is much higher because you don't have so much competition compared to traditional startups. In any case, these kind of projects are, the capital support is very critical to extend the runway, and that's why it's very useful to go to venture capitals or different incubators, accelerators, public funding and subsidies, private contracts, basically everything that would help you to get there so that you can survive while you are developing your product or is helping to in that development phase. And now I would like to also, taking that in mind, I would like to go a bit about our history, how we started and how it has been developing with that mindset of deep tech startup in the last couple of years. So we started, the project itself started already in October 2022. As said, we were coming from the Photonics and RF Research Lab, which is led by Professor Íñigo Molina. It's a very large group in the University in Malaga with over 10 professors and a lot of PhD students. They have over 20 years experience in the integrated photonics, and they have recognized by the Stanford ranking of most prominent researchers. And also, from the very beginning, we were supported by Bullnet Capital, which is a Spanish venture capital firm specializing in deep tech technology, with also over 20 years experience investing in this kind of projects. And they have a very hands-on approach, and they're very close supporting the project from the beginning. And I would like to thank here also the whole team, especially Miguel del Cañizo, Javier Ulecia, that they were from the very beginning really helping us also to get part of this business mindset that I said that we didn't have from the beginning, because at the end we are engineers, so we're not so clear, or we didn't have that knowledge from the very beginning. I must say that this collaboration started already on 2021 because they were working in another spin-off from the same research group, which is Bioherent. So they already, especially Miguel del Cañizo, was already very fond of the technology that the research group was developing, and they wanted to exploit that technology. They really believed that that would be something else that could be getting on from the group. So in the end, we had the support, and we still have the support from both groups. From the one hand, from the one side, the technology development perspective. On the other hand, the business and the entrepreneurship perspective. So, in the first months, we had some transfer of intellectual property. We had the foundation of the company officially in May 2023, and we had the first convertible loan in which we got our first office, and also that was the first step in which we could already focus on the product concept, just looking for potential markets. We were also getting some networking and applying for first non-dilutive funding, just to participate in some missions of Pertachip. Actually, we were one of the first companies in 2023 that we were participating in 2 missions Pertachip at the same time. And also through Bullnet, we had also some networking with some of the other companies that they were applying, like, for example, Leapwave or Fela, among others. On the rest of the year, we completed the management team. We are 3. And we were then focusing, once we had already the technology and more a clear path, really defining to the very last detail the whole business plan, the roadmap, and of course, starting the development, first designs, finding advisors. Also, we were having the help from Bullnet in that aspect. Until February 2024, in which we signed the seed investment led by them, by Bullnet Capital. So through the rest of the year, last year, 2024, then we were already focused mainly in the whole development, just having the first proof of concepts of the first generation of chips, just proving the technology. Also continue with further developments, second generation, already having some basic electronics packaging, and until December 2024, in which we proved we established the first link with 2 chips, just establishing a link in free space. Not only that, but we were also setting the whole optoelectronic laboratory. We had new facilities. Also, we were continuously growing the team, an amazing team of highly skilled and professionals, and also focusing on the development, but also establishing very key relationships with foundries, suppliers, and also starting to check on potential customers. And yeah, this is also according to our technical roadmap, in which last year was the first stones, the foundations to develop the technology, just to prove that our ideas are working. This year we are very focused on the first prototypes, also to have something complete, that integrating also the electronics and so on, and to start also having the first commercial version of the product, of the beta product, in the next year. So one very important point, and also in this presentation, is about the funding. So right now we are in the seed funding that we got by beginning last year. It was 2.7 million led by Bullnet Capital, but also very important was in the whole time is the non-dilutive. Because on the one hand, I mean, we started with searching from all different mechanisms that we could apply to, like subsidies, private contracts, pilot projects, and so on. And this is very important, on the one hand, to extend the runway. So basically, you have you have more time. You are buying time there to develop the project. You are developing also your product in the meanwhile. I mean, you're using those projects to go ahead on the development. But also very important towards a future series, Series A, Series B, and so on, is to raise value. You want to raise value also, not only by the team, also with, for example, the equipment you're having, the products, so that whenever is coming another investment, the evaluation is going to be higher. So you're not diluting yourself so easily. In that case, we raised 1.5 million until 2024, with a 100% success rate in all the fundings we were applying. We had it was divided by 36% private contracts and 64% subsidies. We had said already prototype missions. Also, Neotech was granted, and 2 program Torres Quevedo, etc. And in the meantime, we were also getting some seals and recognitions of the startup, innovative SME, technological-based enterprise, and so on, which have also some advantages in the financial aspects. And one very important thing that is, in the end, is I'm talking about raising, having funds, raising money, and so on. But the most important thing is the team. And I would like also to thank our scientific officers, Íñigo Molina, Alejandro Ortega, Gonzalo Van Wemert, and Robert Hallier, which are part of the university. Also our advisors, and of course, special thanks to Bullnet Capital that have been from the very beginning very close to us. And yeah, we continue growing because, as I just said, the most important asset is your team. This is what you're really building. This is what the people are going to see also afterwards, because it's the key to success. And of course, yeah, we're hiring in case anyone is interested. So.
Okay, thank you so much to Alejandro for this talk. Are there any questions right now for Alejandro? Yes, Pascual.
Thank you, Alejandro, for the nice presentation. So I guess that you have like a technology background, but for some reason, so you are now more also onto the business parts of all this, right? So can you tell us mainly why is this reason? What is that reason that you're now taking more like a role on business, and what has been like the more challenging part of this?
Thank you very much for the question. Well, I must say that I'm still technology manager, so I'm still a very technological guy. Yeah, I mean, I think the main reason is growing. I mean, it's always a challenge, and let's say, not saying that the technological part is easy, but it's something new to learn, it's something very useful. Also going to this path of entrepreneurship and startups, and so I think it's very interesting, and it's something that I would like to not only to learn but really to master, which is it feels much more complicated than everything else about the photonic integrated chips and so on. But yeah, I think it's very challenging, and especially still sometimes getting into different terms, how the difference between some of the concepts that are supposed to be super easy out there, but coming from another world totally different, sometimes it's still confusing. And yeah, I think it's still challenging sometimes. But with time, I mean, at some point, I will learn, so hopefully. Thank you.
Okay, thank you so much for that, Alejandro. Okay, so we have arrived to the end of this session. We would like to thank to all the speakers that participate today and all the people that attended the session. and also, of course, to our sponsors and exhibitors. We are going to have Sandra from SECFO that she's going to give us a couple of instructions for the next B2B meeting. And the people that is interested in the lab tours, there will be some information about that. Thank you.
Okay, so as we told you before, all of you that are interested and signed up for the B2B meetings should be here at the auditorium at 5 o'clock. As you can see on the wall, we have marked the B2B meeting spots. You must look for your number. You can see if your company is on the participant row, and also look at when will be your B2B meeting held and with whom, because maybe you didn't request a meeting, but someone requested a meeting with you. Also remember that these B2B meetings, as we said before, are at the same time that the clean room and lab visits. So yes, some of you already told me that you had these meetings during the lunch break and everything, so if you already talked with the person you were interested in, there's no problem, you can come to me or my colleague Ellie. But if you are still interested in holding these meetings, we are expecting you here. If you have any doubt, we will be projecting this timetable. And if you have any question, anything, we will start 5-ish. So yeah, that's it. Thank you, everyone.
We have two options now, because as Sandra just mentioned, some of you wanted to visit the lab before having, and also having your business-to-business meetings, because we are some advantage in timetable. Maybe we can have now one group to the lab, and then you can have your business-to-business meetings. So please, could you join us, just only the people who is having the business-to-business meetings, and then at 5 we will have another group visiting the labs, okay? Is that okay with you? Is that clear? I'm not sure if it was clear. Yeah, we will meet all together downstairs on the entrance, okay? And then we will separate in two different groups to visit the UPV fab, the clean room fab, and also the characterization lab. Okay? It was clear? Sí? Sí? No? Okay.